Okay, good evening to one and all. So we'll start with a problem on this sequence networks construction, right? Kindly go through this problem once. Yeah, go through this question. Find positive, negative, and zero sequence Thevenin's reactances with respect to generator terminals in bracket bus 1. In bracket bus 1 for the single line diagram shown below. Okay, all the reactances given in per unit form on common base. Generator x1, x2 values 0.2 per unit, x0 value 0.05 per unit. Transformer xt 0.2 per unit, and he said for neutral grounding here, neutral grounding. Let me indicate that here also xn. Anyhow, they have shown that as a resistor, but still they have given the reactance of that. You should treat that as a reactor. Should treat that as reactor, and that reactance value is at 0.03 per unit. Okay, so very simple problem. Very simple problem. You have to calculate. We have to calculate positive sequence, negative sequence, and zero sequence Thevenin equivalent reactances with respect to bus number 1. Okay, so first we will try to draw the positive sequence network of this. Positive sequence network of the single line diagram given. The solution. So first we are going to take a positive sequence network. Positive sequence network. Simple. Generator. How you will represent generator in the positive sequence network? Voltage source in series with its positive sequence impedance. We have studied generator, right? We have seen the per phase network of generator also. Okay. So this generator in the positive sequence represented as a voltage source in series with its internal impedance like this. This is drawn up to neutral. This is drawn up to neutral. I'll call this is positive sequence impedance of generator, and this is some internal EMF of generator EA1. Okay, so it is bus number 1. Bus number 1. Tell me please, how you represent this generator? So transformer in the positive sequence network. All of you have to answer this question. How you will represent this transformer in the positive sequence network? Irrespective of that winding connection. Is it a star delta, delta star, star star, delta delta? Doesn't matter. It is going to be represented as a simple series impedance. Simple series impedance in the per unit domain, right? So irrespective of transformer winding connection, it is going to be represented as a simple series impedance. I will call it is ZT1. Positive sequence Thevenin impedance ZT1. See, this is bus number 2, I will say. And after bus 2, what you have? Simple no load, just open we have. So let me show that also. So simply we have open here. Open. This is the positive sequence network of the single line diagram here. Now your aim is to calculate. Positive sequence Thevenin impedance with respect to bus number 1. So in order to calculate the positive sequence Thevenin impedance, we have to take up this network by killing the sources. So by killing the source, same network I will repeat in this manner. By killing the sources, that network can be redrawn in this manner. It's a node 1. Okay, so it's a generator impedance we'll call ZG1, and this is a neutral terminal, and then you have here ZT1, Okay, and this is bus number 2 we have, and this is open like this way. Now we have to find out the Thevenin impedance with respect to bus number 1. Bus number 1. See, listen all of you, listen all of you. Just check the procedure to calculate the check the procedure to calculate the Thevenin impedance value. Original procedure to calculate the Thevenin impedance value. With respect to which node you want to find out the Thevenin impedance. At that particular node, you keep one current source. Okay, means at node number 1, you assume that we have to keep one current source here. By keeping that current source something like this, don't draw the current source. Just listen. By keeping this current source something like this, check how that current is passing. See, this current will attempt to go in 2 paths. One path is through ZG1 closed. Other path is through ZT1, but it is open. Means ZT1 is not going to carry any current. And this current will flow only through ZG1. And with respect to that ZG1, how much voltage you will get at node 1? That voltage by this current is a Thevenin impedance. This is the exact method to calculate the Thevenin impedance. Else simply by keeping that current source, check which of the impedances are carrying that current. Only those impedances are effective in the calculation of the Thevenin impedance. So simply I can say with respect to node 1, or you can say bus number 1 here, with respect to node 1 or bus number 1, Thevenin equivalent impedance is nothing but generator positive sequence impedance. How much is the generator positive sequence impedance? 0.2 per unit. And one more thing, kindly listen. One more thing. Did he mention anything regarding the base values or anything here? No. But in the problem, he mentioned that all the reactants are given in per unit on common base. So you no need to bother about base selection and all. Okay. And how much is reactance? 0.2 per unit for the generator. Means impedance is how much? J0.2 we have to write. Impedance value was J0.2 in per unit form. J0.2 in per unit form. That's it. Positive sequence analysis is over. Positive sequence Thevenin impedance calculation is over. Next, we draw negative sequence network of the single line diagram, and we'll find out the negative sequence Thevenin impedance. I will say here negative sequence network construction. Simple. Generator. This is a bus 1. I will show. It's a bus 1. How you will represent generator? In the negative sequence network, how you represent the generator? Anybody? Please tell me how you represent generator in the negative sequence network. So simple negative sequence impedance, right? Simple negative sequence impedance between that bus and neutral. Between that bus and neutral, we keep that as a impedance ZG2. We don't have any negative sequence EMF. Okay. After that, bus 1 to bus 2, we have a transformer. Irrespective of transformer connection, transformer will be represented simply as series impedance. Transformer was represented as a simple series impedance with a value of ZT2, and above 2 you have an open circuit like this. Above 2 you have a open circuit. Now you have to find out the Thevenin impedance with respect to bus 1. With respect to bus 1, you have to find out that Thevenin impedance. That is a value ZG2. That's it. Okay, Z Thevenin 2 is nothing but the value ZG2. Okay, I'll write in the next slide. So with respect to bus number 1, you write Thevenin equivalent impedance 2. That is nothing but generator negative sequence impedance. How much is negative sequence impedance of generator? J0.2. 0.2 per unit is a reactance. Impedance means you have to write this as J0.2 per unit. Okay. Now we draw zero sequence network. Zero sequence network of the generator. Sorry, of the single line diagram. Zero sequence network of the single line diagram. Okay, listen kindly. First, you have generator at bus 1. Okay, it's a bus 1. Generator. How you will represent generator in the zero sequence? How you represent generator in the zero sequence? It is a star connected one, right? Star connected one, ungrounded. Star ungrounded. Okay. Up to neutral, we should keep zero sequence impedance of generator. Up to neutral, we should keep zero sequence impedance of generator, and neutral to ground. As it is ungrounded one, we have to keep that 3ZL, means 3 into infinite, it will be infinite. Okay, so I can say up to neutral, up to neutral, we have to keep zero sequence impedance of generator, and then neutral to ground, we have to keep 3 times of Zn, which is infinite, open circuit. Next one, bus 1 to bus 2, what we have? Bus 1 to bus 2, we have a transformer. We have to think about the connection of transformer before drawing this zero sequence net. So first, what we will do is, between bus 1 and bus 2, I'll show this bus 2. Between bus 1 and bus 2, I'll keep an open diagram with ZT0. Keeping this open diagram as ZT0, zero sequence impedance of transformer. Primary what connection we have? Star grounded. Star grounded means series switch on the primary side has to be closed with 3 Zn. Star grounded means series switch on the primary side should be closed with 3 times of Zn. So I will be showing 3 times of Zn here by closing the series switch on the primary side. What's the secondary winding? Delta. Delta means what? Shunt switch will be closed with zero impedance. Means I can say shunt switch will be closed in this manner. Now, with respect to bus 1, we have to find out that Thevenin impedance. With respect to bus 1, we have to find out this Thevenin impedance. Yeah, if you look at with respect to bus 1, means again the same rule, what I said here. You inject some current at bus 1. Inject some current at bus 1, and that current will see two paths. One path is flowing through this generator, open circuit, it won't flow in this one. And the other one is flowing through this transformer, means only transformer impedance along with 3 Zn will come in the zero sequence Thevenin equivalent network. Okay, so I'll write with respect to bus number 1, with respect to bus number 1, Z Thevenin naught, nothing but ZT naught plus 3 times of Zn. 3 times of Zn. Till now, in the positive and negative sequence networks, you don't have any effect of transformer. You don't have any effect of the transformer. But in the zero sequence network, you have the effect of only transformer and you don't have the effect of the generator. Okay, so how much is the value of ZT0? How much is the value of ZT0? Let's look into the data. ZT0 is J0.2. ZT0 number is J0.2 plus 3 into, what is Zn number? What is Zn? Xn 0.03 na? Zn means J0.03. J0.03. This number will come as J0.29 per unit. Z Thevenin not equals to J0.29 per unit. Okay, so like this, you can find the positive, negative, and zero sequence Thevenin equivalent impedances. What he asked, reactances or impedances in the question. What he asked in the question. He asked only reactances, right? You write only reactance numbers. Okay, so XTH1 0.2 per unit. XTH2 0.2 per unit. XTH0 0.29 per unit. See, sometimes maybe in while we are writing the equations and all, sometimes I'll call that Z Thevenin 1 as Z1 equivalent. Positive sequence Thevenin equivalent impedance. Z1 equivalent. I will use these two terms synonym. Okay, Z Thevenin 1 or Z1 equivalent, both will give same meaning. Similarly, Z Thevenin 2, I can write it as Z2 equivalent. Z Thevenin naught, I will write it as Z0 equivalent. Z0 equivalent. Similarly, here also, this you can say X1 equivalent, positive sequence Thevenin reactance. This is negative sequence Thevenin reactance, and this is zero sequence Thevenin reactance. Like that, we can say. Okay. So next, what we do is we'll take transmission line. So how to construct positive, negative, and zero sequence networks of transmission line, that I will discuss. Sequence networks for transmission line, 3-phase transmission line. So 3 Zn is equals to infinite means for star grounded, it should be star ungrounded, right? Star ungrounded, it is open. Yeah, yes, Vinita. Yeah. So I have already uploaded these questions in the student portal. Just you download it and see Imtiaz. Imtiaz. Already I have uploaded these questions. So I'm showing previous slide. If somebody is still writing, please complete it. Okay. Done. So let's move to transmission line, three-phase transmission line. Sequence networks for three-phase transmission line. Sequence networks for three-phase transmission line. Okay, I will take three wires, phase A, phase B, phase C first. It's a phase A wire, transmission line wire, phase A. And it's a phase B transmission line wire. And we have phase C transmission line wire, something like this. Okay, so this is A, B, C. And we have ground as a reference. Ground as reference. I'm showing that. Ground reference. Reference. You can call this as ground. Ground reference. Next. See. Yeah, listen. See, each line is having a self-impedance of ZS. Each line, A, B, C, each line having a self-impedance of ZS. Else, I will tell in a general way, thereafter I will take the assumptions. Okay. I'll call self-impedance of A conductor, ZAA, self-impedance of B conductor, self-impedance of C conductor, ZAA, ZBB, ZCC. Mutual impedance between A and B. Because generally, if two conductors are there, one beside the other, having some mutual linkages between them, definitely some mutual inductance will exist between the two conductors. Or it is a mutual impedance will exist between the two conductors. That's why between A and B, I will call that mutual impedance as ZAB. Between B and C, I will call that mutual impedance as ZBC. Between C and A, I'm calling that mutual impedance as ZCA. I will write in the next slide the same statements what I have mentioned, right? ZAA, comma, ZBB, comma, ZCC. These are self-impedances. And similarly, ZAB, ZBC, ZCA, these are going to be called as mutual impedances. Mutual impedances. Okay, next thing. Next. Input side, sending end side. Voltages I am saying. Voltage means voltage of ABC with respect to ground. Voltage of ABC with respect to ground. I am showing for phase A conductor, it is VA. VA. So top positive, bottom negative. Conductor B, it is VB. Positive, negative. And for C, it is plus minus VC. VC. Okay, these are input voltages, or you can say sending end side voltages. At the receiving end side, we have voltages like VA dash, VB dash, and VC dash. Conductor A voltage, I am calling as VA dash. Conductor B voltage, we are naming as VB dash. Conductor C voltage, we are calling this as VC dash. Okay, like this we have the input and output voltage of transmission line wire. Transmission line wire. Yeah, next thing. 1 minute, please. Yeah. Next, listen here. So first what I will say is all the three conductors might be having equal size. All the three conductors might be having equal size. So that I will assume that this ZAA, ZBB, ZCC numbers are equal. So that we will say as ZS, self-impedance of any one of the line conductors. Okay. So I'll write let the size of each conductor is equal. So by making that assumption, ZAA value equals to ZBB value equals to ZCC value, which is nothing but ZS, self-impedance of any one of the line. Next one. Let us assume that. Next assumption, please look here. Let us assume that distances between the conductors, means between AB, between BC, between CA are equal. Okay. If the distances between the conductors are equal, then we will say this mutual impedances ZAB, ZBC, ZCA values will be equal, obviously. Okay. So next I can write when we can say distances between the conductors will be equal. When we can say distances between the conductors will be equal, if the conductors are in the symmetrical spacing. If the conductors are in the symmetrical spacing. Else, we have one more thing to say: unsymmetrical transposer system. Unsymmetrical transposer system. So for symmetrical spacing system or unsymmetrical transposer system, I can say these three mutual impedances will be equal. Okay. Yeah. So for symmetrical spacing or unsymmetrical transposed system, mutual impedances between the conductors will be equal. ZAB equals to ZBC equals to ZCA. I'm calling this as ZF. Calling that as ZF. Okay. Next thing. Listen, please. Next thing. See, actually, our aim here is to find out positive, negative, and zero sequence impedance of the transmission line per phase. So for that, before moving to that exactly, I want to write these equations. Voltage drops. What is the phase A voltage drop? VA minus VA dash. Input voltage minus output voltage. Phase B voltage drop. VB minus VB dash. Similarly, VC minus VC dash. I will try to write them, right? After that, I will convert these voltage drops into symmetrical components. Then we will try to know how much impedance is offering voltage drop for positive sequence current. How much impedance is offered for negative sequence current? How much impedance is offering for zero sequence current? That's it. Okay, fine. So first I will write voltage drops in the three wires. Voltage drop equations. Voltage drop equations. Voltage drop equations. So it is VA minus VA dash. VA minus VA dash. What you can say VA minus VA dash? First you see currents. I forgot to give you currents. Let me show those currents here. Phase A current IA. Phase B current is IB. Phase C current is IC. Listen. Very simple thing. Just by following a simple logic, we'll write it. Self voltage drop. Self drop in this conductor IA into ZAA. IA into ZAA. Next. We have some mutually induced EMF in conductor A due to B. We have a mutually induced EMF in conductor A due to B. That's also a voltage drop in A. How much is that? The current in B, IB, into that mutual impedance ZAB. Okay. And similarly, due to C also, we have some drop in the conductor A. So that we can say IC into ZCA. Okay. So what is the self voltage drop? IA into its self impedance. Mutual drop due to B, IB into that mutual impedance between B and A. Next, due to C, IC into mutual impedance between C and A. Okay. So I'll write here IA into ZAA. In place of that ZAA, I will keep simply ZS. Due to conductor B, IB into mutual impedance already we assumed as ZF. Due to conductor C, I'll write IC into ZF. Sum of these three voltage drops is gap between input and output voltages, VA minus VA dash. Next one. Similarly, we write VB minus VB dash also, voltage drop. VB minus VB dash. Tell me first, what is self drop in the B? IB into ZS. IB into ZS. Due to A, IA into ZM. Due to C, IC into ZM. Okay. So that I will write in an order. I will write in an order. IA into ZM plus IB into ZS plus IC into ZM you can get. Like, and similarly, what is VC minus VC dash? I will have self drop due to C, self drop due to C. So IC into ZS I can say. Mutual due to A, IA into ZM. Mutual due to B, IB into ZM. Okay. So I can write here IA into ZM, IB into ZM, and due to C, I can say IC into ZS. IC into ZS. Okay. Yeah. Yeah, Shivkumar, already we have made that assumption, right? Is ZCI is less than ZBC. That's not thing. Already we assumed that all the three mutual impedances are equal. Okay, by assuming symmetrical spacing. Next. As a notation, this VA minus VA dash I am calling as delta VA. VB minus VB dash delta VB. VC minus VC dash delta VC. Okay, I'll write these equations in a matrix form. Writing these equations in matrix form. Kindly go through it. Delta VA, delta VB, delta VC. Voltage drops in the lines ABC. Next, here we have impedances, and then here it is IA, IB, IC. IA, IB, IC. And here impedances will be ZS, ZM, ZM, and then you have ZM, ZS, ZM. And this will be again ZM, ZM, ZS. Like this you have. Okay. Now this delta VA, delta VB, delta VC, that vector I am going to call as delta VABC, voltage drop vector. Delta VABC, voltage drop. And you have self and mutual impedances in this matrix that I am going to name it as ZABC vector. ZABC vector into, you have currents in that column IA, IB, IC, that I am going to call as IABC vector. That I am calling as IABC vector. Yeah, simple, very, very simple. From this point, we are going to apply symmetrical components on this set of equations. That's it. We are going to apply symmetrical components on this set of equations. See, I said earlier, symmetrical components we can apply only on phasors. Only on phasors means we said voltages we can apply, on currents you can apply, fluxes you can apply, and you can apply on voltage drops also. Voltage drops. But you can't apply this on the impedances. On the impedances. What is the meaning of that? Means, listen here, listen. For example, if you have voltages like VABC phasor, this you can rewrite in terms of symmetrical components equivalent as A into V012. Like this you can rewrite. That's the meaning to say on voltages we can apply the symmetrical components. But I said on impedances you can't apply, in the sense you can't write ZABC is equals to A into Z012. This type of matrix you can't write for the impedances. This type of matrix you can't write for the impedances. All of you understood this meaning what I am saying? Symmetrical components can be applicable on set of phasors, means that phasor set you can write it as A into symmetrical components of the same phasors. But you can't write the impedances ZABC vector as A into Z012. That type of thing you can't write. All of you getting me? So now my interest is to write from this point delta VABC. Delta VABC I will replace with A, matrix A into delta V012. Means phase A, phase B, phase C voltage drop set we are going to convert into sequence voltage drops. Sequence voltage drops. Similarly, this IABC we will be replacing with A into I012. A into I012. Okay. So by symmetrical components. If you want, you can keep this one aside, else you can skip this. Okay, I'm removing this one. I'm removing this one. By symmetrical components, by symmetrical components, you can write delta VABC vector is equals to A into delta V012. Like that, you can make that replacement. Similarly, current vector IABC, you can replace with A into I012. A into I012. Okay. So now, therefore, this previous vector set what we have, that you can replace as A into delta V012 vector, nothing but ZABC impedance vector 3 by 3 matrix. ZABC impedance vector 3 by 3 matrix. Into that IABC, you can write as A into I012. A into I012. And now, simply this matrix A, I will take to the other side. But better what to say is multiply with A inverse on both sides. Multiply with A inverse on both sides. If you do that multiplication, left side you get delta V012 only. Right side, you get A inverse first. A inverse into ZABC into A. A inverse into ZABC into A multiplied with I012. Multiplied with I012. Delta V012 equals to A inverse into ZABC into A into I012. Okay. Now, this is nothing but sequence voltage drops. This vector represents the sequence voltage drops. Means positive sequence voltage drop, negative sequence voltage drop, zero sequence voltage drop. And these are sequence currents, sequence currents. Then who will give the relationship between the sequence voltage drops and sequence currents? Sequence impedances of transmission line. Means this A inverse into ZABC into A. This matrix will consist sequence impedances. Okay. So it consists sequence impedances. Sequence impedances. I'll call this as Z012. I'm calling that as Z01. Okay. So simply you take that A inverse, ZABC, A, multiply them together. By that way, you are going to get the zero sequence, positive sequence, and negative sequence impedances. Okay, already you know matrix A, ZABC also you know, A inverse also you know. So just try attempt to get that Z012 matrix. I'll come back within 1 minute. Please try to get this Z012 matrix. So I have resumed audio, video, and screen. Yeah, let's move with Z012 calculation. As I said, you Z012 calculation. So I can write here sequence impedance matrix Z012 is equals to, first we have A inverse, right? Matrix A inverse that you have already seen in the symmetrical components, which is 1 by 3, 1, 1, 1, 1 alpha, alpha square, 1 alpha square, alpha. This one here. And ZABC matrix, you have ZS, ZM, ZM. And you have again ZM, ZS, ZM. Again, it will be ZM, ZM, ZS. Okay. And this multiplied with matrix A. Matrix A means 1, 1, 1. 1 alpha square alpha, 1 alpha alpha square. 1, 1, 1, 1 alpha square alpha, 1 alpha alpha square. Okay. Yeah. Next. Listen. So you go with this multiplication and all. I am going to write the final solution what we get. Of course, we get 3 by 3 matrix in the final solution. That is nothing but ZS plus 2 ZM, you get one number. 0, 0, 0. You get here ZS minus ZM. 0, 0, 0. Again, you have here ZS minus ZM. See, these are the sequence impedances by neglecting the ground effect. Kindly observe my words, what I am saying. By neglecting the ground effect. Anyhow, you please leave that statement. I will write that ground effect later. Okay. So Z012 is this one. And simply, I will keep this matrix in that 3 by 3 matrix set. Delta V012 means delta V0, delta V1, delta V2. Okay. So you take this as equation 2. Equation 2. This is equation 1. Equation 1 is in terms of ABC. Equation 2 is in terms of 0, 1, 2. That equation 2 we are going to rewrite. So equation 2 can be rewritten as observe here delta V012 in the sense 0 sequence voltage drop, positive sequence voltage drop, negative sequence voltage drop. Okay, so this is equals to Z012 matrix ZS plus 2 ZM. We have 0, 0, 0, ZS minus ZM, 0, 0, 0. You have again here ZS minus ZM, and this multiplied with you get IA0, IA1, IA2. IA0, IA1, IA2. Else you write del I0, I1, I2 also. I0, I1, I2 also. Okay, simple. This delta V0, nothing but VA0 minus VA0 dash. VA0 minus VA0 dash. Delta V1 is VA1 minus VA1 dash. And delta V2 is VA2 minus VA2 dash. VA2 minus VA2 dash. Okay. Now you write the three equations. First, 0 sequence drop equation. VA0 minus VA0 dash equals to ZS plus 2 ZM into IA0. Similarly, VA1 minus VA1 dash, and then VA2 minus VA2 dash. Okay. So let's move to the next slide to write those equations. Okay. Yeah. So I'm taking in the next slide. First, 0 sequence voltage drop equation. VA0 minus VA0 dash ZS plus 2 ZM into 0 sequence, correct? VA1 minus VA1 dash ZS minus ZM into positive sequence, correct? VA2 minus VA2 dash. Again, you have ZS minus ZM into negative sequence, correct? Negative sequence, correct. Okay. Yeah. One small request to you. Anyway, I will be uploading these notes at the completion of class itself. Maybe if the class completes at 10 o'clock, I might be uploading these notes within 10 minutes or within 20 minutes in the portal, right? I am giving that in the Telegram also. My kind request is, please go through the previous sessions, what I have discussed. before attending the next session. Revise the notes. Revise the notes before attending the next class to have a proper interlinking as well as proper understanding. Okay? Yeah. Next. See this. See, by using these three equations, I will try to construct the networks. First, I will say positive sequence per phase network of transmission line. Positive sequence per phase network of transmission line. Simple, very simple. Input voltage VA1, output voltage VA1 dash. Current flow IA1. Drop, voltage drop is IA1 into ZS minus ZM. So, simply, I will keep some impedance between input side and output side. Input side voltage VA1, output side voltage VA1 dash, and current is flowing in this particular direction. Impedance of this is ZS minus ZM. That's it. And the ZS minus ZM is nothing but positive sequence impedance per phase. Nothing but the positive sequence impedance per phase. Next one. Negative sequence network will draw in the similar manner. Negative sequence network. Again, input voltage VA2, output voltage VA2 dash. Input voltage VA2 here. Output voltage is VA2 dash. Okay. Current is IA2 in the branch. Impedance I will keep ZS minus ZM. That is nothing but the negative sequence impedance Z. If you want, you write the equation from network again, it should satisfy the derivative equation. What means VA2 minus VA2 dash is equals to IA2 into ZS minus ZM. VA2 minus VA2 dash equals to IA2 into ZS minus ZM. Similarly, zero sequence network also we can show. Zero sequence network also you can show network, right? So you keep some impedance in this branch, and this voltage is VA0, zero sequence voltage, and this voltage is VA0 dash. Okay, current in this branch is IA0 here, and this impedance is ZS plus 2ZM, ZS plus 2ZM, and this impedance is nothing but Z. So positive sequence impedance and negative sequence impedance of transmission line are equal. Positive and negative sequence impedance of transmission line are equal. ZS minus ZM only, whereas zero sequence impedance of transmission line is ZS plus 2ZM. ZS plus 2Z. Okay. With respect to what, can you please elaborate? What's your doubt, Muthireddy, Vasista? Please elaborate your doubt. Yeah. So now I can write in the next slide, or here itself I will write positive sequence impedance of transmission line, negative sequence impedance of transmission line, both are equal to ZS minus ZM number, whereas zero sequence impedance of transmission line is ZS plus 2ZM number. ZS plus 2ZM. ZS plus 2ZM. Okay. Next thing I want to tell. How is the value of Z0 compared to Z1 and Z2 from this? How will be the value of Z0 compared to Z1 and Z2? So does these sequence voltages are with respect to reference ground? I am asking. Okay, good. Muthireddy, this is with respect to zero potential, you can say neutral. This is again with respect to neutral, but this is with respect to ground. That's with respect to ground. What is this neutral you are saying, sir? You may not have analysis only on transmission line, right? You have some other equipment connected like generator, transformer and all. That neutral line is a reference for these two networks. Whereas ground is a reference for the zero sequence network as it is we have discussed earlier. Okay, how is the value of Z0? ZS plus 2ZM definitely comes greater compared to ZS minus ZM. So always for transmission line wire, zero sequence impedance will be greater compared to positive and negative sequence impedances. Okay. Yeah. So in the next slide, I am showing always for a practical transmission line wire, zero sequence impedance is greater compared to Z1. Zero sequence impedance is greater compared to Z2. Of course, I said Z1 equals to Z2. Generally, the zero sequence impedance of transmission line will be in the range of 2.5 to 3.5 times of Z1. Generally, Z0 will be in the range of 2.5 times Z1 to 3.5 times Z1. But typical number, if you want to take anywhere, you can choose that number 3 times of Z1. Typically, zero sequence impedance of line will be 3 times of Z1 for transmission line. Okay, transmission line. Next thing. Practically, in the sense, dear Sajan Singh, practically in the sense, for example, I'll tell you, if we don't have mutual linkages between the conductors, if I say that there are no mutual linkages between the conductors, is it practical or theoretical? We have 3 conductors, right? Conductor A, B, C, and I say there are no mutual linkages between the conductors. What do you mean by that? Is it theoretical one or practical one? Theoretical or practical? Theoretical, right? Because practically speaking, definitely there exist mutual linkages between the conductors. See, Sajan Singh, if we have that mutual linkages between the conductors, definitely ZM value will exist. If ZM is existing, listen to me, if ZM is existing, then only Z0 will be greater compared to Z1 and Z2. If you don't have ZM value, then Z1, Z2 will be ZS, Z0 will be again equals to ZS only. Understood my statement, what I made here, practical line? Is it clear? ZM will not be 0 ideal case or practical case, whatever it is. Yeah. Next thing. The next thing what I'm going to discuss here is a bit confucius. Little confucius, but I will try to make it clear. Okay? Yeah. For example, don't make any changes. Anyhow, as a chance is there, I'm copying these equations, whatever it is necessary. For example, these are the voltage drop equations in terms of ABC. Okay. Before moving to this also, I'll tell one more thing. How many equations you need to solve in the ABC? You tell me here. You tell me how many equations I have to solve. Yeah. How many equations you have to solve in the ABC system? 3 equations, phase A, phase B, phase C. After converting this set of ABC equations into symmetrical components, how many equations you have to solve? After converting set of 3 equations into symmetrical components, how many equations you have to solve now? Again 3 only. Imtiaz, just go with this. What I have written. Also 3 means the symmetrical component transformation will not change number of equations to be solved. Okay, that is one conclusion. If you want, you can write. Okay, so I'll write here itself. The symmetrical component transformation. The symmetrical component transformation will not change number of equations to be solved. It will be remains 3 only. Okay, next thing. But calculation is easy. In what way it is easy, Ashish and Danvi? In what way it is easy? See, if you think about these ABC equations, how these 3 equations are coupled together, right? If you want to solve only first equation, you can't solve it. If you want to solve only second equation, you can't solve it. You have to solve all the 3 equations simultaneously. That is a dependency on one another in the ABC components. But if you convert them into symmetrical, how these 3 equations are coming? Uncoupled equations. That's what I mentioned earlier at the beginning of the symmetrical components itself. Right? With the help of symmetrical components, what is it? With the help of symmetrical components, we are capable to convert set of coupled equations into set of uncoupled equations. Okay, all of you getting this one? When the conductors are carrying or when the system is carrying balanced currents. System is carrying balanced currents. Yeah, sorry, unbalanced currents. Unbalanced currents. Yeah. So I'll write that statement also here. So with the help of symmetrical components, set of coupled equations, in bracket ABC can be converted into set of uncoupled equations, right? 0, 1, 2, and solving those equations will be easy. That implies analysis will be easy. Analysis becomes easy. That's the thing what we are going to achieve with the help of the symmetrical components. Okay, all the comments are over. Now we are entering into some other topic here. Other topic in the sense, in the same, other confucius thing little bit. Okay. Listen, please. Listen. You know, this first number is a mutual impedance between AB. Second number, mutual impedance between AC. Similarly, these are mutual impedance between CA. Sorry, BC. See, earlier we assumed that these mutual impedance are equal. AB mutual impedance, BC mutual impedance, CA mutual impedance equal. Now, if these mutual impedances are unequal like this, Zm1, Zm2, Zm3, unequal numbers. If these mutual impedances are unequal numbers, then if you are attempting to calculate this Z012 matrix, kindly look here. I'll copy that also to this slide. If you are attempting to get the Z012 matrix 1 by 3, 1, 1, 1, 1 alpha, alpha square, 1 alpha square, alpha, A inverse. And here ZABC na Zm1, Zm2, Zm3, Zm1, Zm2, Zm3. And here it is A. If you go with this multiplication, definitely you don't get this number 0. This number will not be 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 0. And this is Z0. You get some other value. May not be ZS plus 2ZF. A different number you used to get here. And here you may get a different number Z1. And here you may get a different number Z2. And the Z1, Z2 may not be equal. Z1, Z2 may not be equal. Yeah, all of you getting this slide? You no need to write. Just listen here. Getting Zm1, Zm2, Zm3. If you take mutual impedance as unequal, then you are getting all these impedances. Then if you want to write this resultant equations in symmetrical components, how these things will get now? How these things we are going to get? Means this set if you consider, and all these zero values will not come. Means all these values will be non-zeros. All these numbers will be non-zeros. Not only that, Z0 is not equals to that number, Z1 is not equals to that, Z2 is not equals to that, and not only that, that Z1 and Z2 may not be equal. Okay, then how these equations are coupled equations only? Even after using symmetrical component transformation, you are getting the resultant equations as coupled only. Are you getting any advantage of the symmetrical components in this particular case? Are you getting any advantage of symmetrical components in this particular case? Yes or no? Right? So we are not getting any advantage of the symmetrical components. See, particularly, when I will say these mutual impedances are unequal, if the conductor system is unsymmetrical, untransposed one, then the symmetrical components will not give any advantage to us in the network analysis. Okay? Yeah. So I'll write that implies resultant equations are coupled. Resultant equations are coupled equations only, coupled, and no advantage of using symmetrical components in untransposed unsymmetrical line, untransposed unsymmetrical line, untransposed. We are not going to get any advantage of the symmetrical components, right? Okay. All of you stop writing. All of you, please stop writing. Just think about my question, what I am asking you now. Symmetrical component analysis will give its advantage on balanced networks or unbalanced networks. Symmetrical components will give its advantage on the balanced networks or unbalanced networks. Anybody? Okay, all of you are saying unbalanced network, that's okay. See, unsymmetrical line means, can I say phase A, phase B, phase C impedance are unequal? If it's unsymmetrical line, mutual impedances between the conductors are unequal. So definitely phase A, phase B, phase C impedance are unequal. Then obviously your network is unbalanced, right? If the network is getting unbalanced, listen please, listen to my words. Remove all things from your mind. Remove all things from your mind. Just listen to me. As a mutual impedance are unequal, obviously phase A, phase B, phase C will not have equal impedances. If the phase A, phase B, phase C are not having any equal impedances, then definitely I will say the network is unbalanced. On that unbalanced network, if you are applying symmetrical components, you are not getting any advantage. Okay, so we will get the advantage of symmetrical components if you apply that on the balanced networks only. On the balanced networks only. Then why we are studying this? If the network is balanced, then obviously you can do surface analysis, right? But I will say this word: network is balanced, but carrying unbalanced voltage and currents. Network is balanced, but it is carrying unbalanced voltage and currents. That's the thing we have to understand now. Okay? Yeah. So I will explain. I will explain to you. Just listen here. For example, we have a generator. Generator is having phase A, phase B, phase C impedances exactly equal. ZA, ZB, ZC are equal. Can I say it's a balanced network now? Generator alone. It's a balanced network? Yes. Transformer. Also having ZA, ZB, ZC equal. Phase A, phase B, phase C impedances exactly equal. Can I say transformer is a balanced one? Balanced network? Yes. Transmission line. It's also symmetrical line. Symmetrical transmission line. So obviously, if it's a symmetrical line, phase A, phase B, phase C impedances will be exactly equal. Phase A, phase B, phase C impedances are exactly equal. But whatever the load we are connecting here, this load is unbalanced one. This load is a unbalanced one. So what is a network supplying to this load? What is a network supplying to this load? This one. It is a balanced network. Supplying an unbalanced load, in the sense balanced network carrying unbalanced voltages and currents. It is having unbalanced voltages and currents because of the unbalanced load what you kept at the end, and as a whole system, I would say unbalanced system. But with respect to the point of unbalance, your network of generator, transmission line, transformer, this is a balanced network for us. Yeah, anybody having a doubt in this? Please kindly tell me. Balanced network carrying unbalanced voltages and currents. Unbalanced voltages and currents. Voltages and currents. Yeah, correct. Amrit, correct. Yes, yes, Shivana. Yes, Shivana. Listen here. Means, listen, whenever you are drawing positive sequence network per phase. Positive sequence network per phase. Definitely, generator should have equal impedances in the three phases. Transformer should have equal impedance in the three phases. Line should have equal impedance in the three phases, right? Then only we can draw the positive sequence network per phase. Similarly, whenever you are drawing negative sequence network per phase, generator should have equal impedance in the three phases. Transformer should have equal impedance in the three phases. Line also should have equal impedance in the three phases. Then only we can draw negative sequence network per phase. Similarly, zero sequence also. After drawing positive sequence network per phase, negative sequence network per phase, zero sequence network per phase, we have to give connections among these three by following the conditions of the unbalanced loading. Are you clear about this? So the final conclusion, what we can say is symmetrical components will give advantage, or will make the analysis simple, will make the analysis simple if the balanced network is carrying unbalanced voltages and currents. Unbalanced voltages and currents. Voltages and currents. Of course, I have repeated the same statement down also. Okay. Why can't we write Z as Z0 plus Z1 plus Z2? Vishnu Ajit, anywhere do you get that type of result? See, simple. Whenever you are adding impedances together, either it should come from some equation to you. Yes or no? If it is not coming from any equation or from the application of KVL, KCL, you should not just add the numbers together, right? Is this clear, Vishnu? Yeah. Fine. So this is about the sir, if load is balanced, then no advantage. No advantage means if load is balanced, you can do per phase analysis only, right? I don't say no advantage. It is not required to go for symmetrical components. You can do directly per phase analysis. Unbalanced voltages means it's with respect to terminals. Yeah, Pratyush Punyapu. This generator is having three impedances equal, phase A, phase B, phase C. Transformer also having equal impedances. Line also having equal impedances. But terminal voltages are unbalanced, carrying unbalanced currents. Terminal voltages are unbalanced, carrying unbalanced voltages and currents. Carrying unbalanced voltages and currents, terminal voltages are unbalanced. That's the meaning here. Okay? Yeah. So finally, anyway, we don't discuss about this unsymmetrical line. So basically, if in the examination, anywhere if they say simply transmission line wire, we have to assume it as a transposed and a transposed or it's a symmetrical spacing. If they want to ask a question, on unsymmetrical line, untransposed one, they will mention that in the question. Unless otherwise, simply anywhere, just you say simply three-phase transmission line having certain impedance something. You have to assume that line is symmetrical line or line is unsymmetrical transposed one. Clear? Okay. Now I want to make a sort of conclusion between the three apparatus what we have studied with respect to their sequence impedances. Yeah. So I will show one small table to you. So it's apparatus name, and sequence impedances on the other side. Sequence impedances. First, tell me generator, or you can say alternator, or you can call simply synchronous machine also. Synchronous machine also. How are the Z1, Z2, Z0 for the alternator? Anybody? Z1, Z2, Z0 for the alternator. How are the Z1 and Z2 numbers? Maybe close. We have studied yesterday, right? Z1, Z2 will be a bit close. How is the value of Z0 number? It will be definitely less compared to Z1 number. Definitely less compared to Z1 and Z2 numbers. Okay, next one. Transformer. Transformer. How are the values of Z1, Z2, Z0 here? Neglect the neutral impedance for time being. Neglect the neutral impedance for time being. What if the network is unbalanced? We don't get any advantage of the symmetrical components. I said already, Pujar, why you are typing the same question again and again? I said you in the previous class also, if you type, definitely I will notice the thing. Okay, listen please. Next, for transformer, how are the values of Z1, Z2, Z0? All the three will be equal. Transformer, I can say Z1, Z2, Z0 will be equal without considering the neutral impedance. We are saying only winding impedance. We are saying only winding positive sequence, negative sequence, and zero sequence impedance in the per unit domain. Next one. Recently, we studied about transmission line. How are the Z1 and Z2 for transmission lines? How are the Z1 and Z2 for transmission line? Equal, whereas Z0 is very high compared to Z1 and Z2. Yeah, see, unbalanced condition may occur during fault as well as even under normal operating condition also, there is a chance of getting the unbalanced operation. Okay? Yeah. So anyhow, Z1, Z2 are equal for transmission line with the conditions what I have mentioned, and Z0 is greater compared to Z1. Z0 is greater compared to Z1. Now, for example, so I have one apparatus with certain impedances. I will show that. Just listen. Yeah, so I'm showing you the next slide. For example, an apparatus have sequence reactances or sequence impedances. Sequence reactances, you say. X1, 0.2 per unit. X2, 0.21 per unit. X0, 0.12 per unit. What is that apparatus? What might be that apparatus type? Anybody? What might be that apparatus type? According to that X1, X2, X0 values given, what might be that apparatus type? It might be alternator. What is the best way of comparison? What is the best way of comparison always? It is to compare the value of zero sequence impedance with a positive and negative. Because you see that itself is discriminating these three apparatus here. In case of alternator, you know, Z0 is low compared to Z. In case of transformer, you know, Z0 is equals to Z1. Whereas in case of line, Z0 is greater compared to Z. Okay, so here X0 is less compared to X1. So this apparatus may be alternator. Apparatus may be alternator. Alternator. Okay, so next I will give this as a question to you. Next one, I'm giving this as a question to you. An apparatus has X1 equals to X2 equals to X0, 0.1 per unit. X1 equals to X2 equals to X0, 0.1 per unit. Which of the following is that apparatus? Following is that apparatus. Which of the following is that apparatus? So I'm giving options here. Kindly go through the options, what I'm saying. Option A, alternator without armature reaction. Without armature reaction is option A. Option B, transformer. Option B. I am writing option C. line with transmission line without mutual linkages. Transmission line without mutual linkages. Without mutual linkages. And option D, all the above. All the above. Yeah. Tell me, what's your answer for this? What's your answer for this one? All. I think all of you getting the reason why the sequence impedance are becoming unequal from one equipment to other equipment. Okay. Alternator, why we have some differences between the reactances due to armature reaction. Transformer, no armature reaction, all the three are equal. Line, why you are getting unequal? Because of mutual linkages. If you don't have mutual linkages, all the three impedances will be equal to ZS itself. So your answer will be obviously D here. All the above. So correct answer here is D. All the above. Okay, next. So next we'll be looking one problem on transmission line first. Transmission line. After that, we will move on to sequence networks construction. Some problems. So maybe 2 or 3 problems we will discuss on that. Okay. Yeah. So let us say the next slide. So to go through this question once. There. It's not there. Yeah. Go through this one. I want to tell some more thing to you with the help of this problem. I want to tell some more thing to you with the help of this problem. I think already this problem is there in your file, PDF file. Go through that. Go through it. Three-phase symmetrically spaced transmission line. Three-phase symmetrically spaced transmission lines are practically sequence. Yes, we have some experiments to measure the sequence impedances. Transformer, why not? I didn't get your doubt, Urup and Satish. Yeah. Look at this. Three-phase symmetrically spaced line has 4 wires, A, B, C, and then neutral. Okay. With sequence impedances Z1, positive sequence impedance, equal to negative sequence impedance J10 ohms. Zero sequence impedance is J40 ohms. Neutral wire impedance is J3. Neutral wire impedance is J3. The magnitude of the self impedance of each phase wire is how much? See, we have a 3-phase 4-wire system here actually. This is a phase A conductor, and it was a phase B conductor, and it's a phase C conductor, and I am showing one neutral wire also. Neutral wire also like this. Okay. So we have to make one assumption here. I will tell you that assumption before writing that solution. Neutral. Between ABC are having some self impedances like ZS. ABC are having self impedances like ZS. This neutral wire is having a neutral impedance of ZN given in the data. ZN number is at J3. Between AB, we have a mutual ZAB. Between AB, we have a mutual as ZAB, else you write ZN. BC, between these two, we have ZN. And between A and C also, we have a mutual impedance of ZN. Like this, we have mutual impedances between the branches. And the assumption now, what I am taking is no mutual linkages between neutral wire and ABC conductors. That's the assumption. That's the assumption, even though they have not given in the problem. I'll write in the next slide. Assume that no mutual linkages exist between neutral wire and phase conductors. Neutral wire and phase conductors. This is an assumption we are making. assumption we are making. Okay. Let's look here. See, if that's the case, first of all, if you write positive sequence impedance of this one, see, whenever you are calculating positive and negative sequence impedances, neutral impedance will not show any effect. That you know, neutral impedance will not show any effect. Why? In the sense, for positive sequence current, no current flow in the neutral. For negative sequence currents also, no current flows in the neutral. Neutral current will exist only for the zero sequence current. That's why on Z1 and Z2, we don't have any effect of this neutral impedance. So it will be simply Zs minus Zm. Z1 equals to Z2, that is simply Zs minus Zm. But if you take up this Z0, earlier equation, you know, Zs plus 2Zm. Now the 3 times of Zn will be added to this. 3 times of Zn will be added. Okay. Now from the values given, Zs minus Zm, Z1 value J10. Zs plus 2Zm plus 3Zn is equals to J40. Zn value J3. Substitute the numbers, try to get the value of Zs. Okay. Yeah. So let's write. Therefore, from the data, Zs minus Zm equals to J10 ohms. You call it equation 1. Call that as equation 1. Okay. Next, Zs plus 2Zm plus 3 times of Zn equals to J40. Okay. And you write Zs plus 2Zm plus what is the 3 times of Zn? 3 times of Zn means J9. J9. You write here Zn equals to J3 ohms. So this is J40. From this, Zs plus 2Zm is equals to J31 ohms. J31. You solve equations 1 and 2 together. Maybe you take multiplication of equation 1 with 2 and add with the second equation. We'll get that Zm cancellations and we'll get Zs value. Okay, simple mathematical calculation we are doing. So equation number 1 into 2 plus equation number 2. What is equation number 1 into 2? 2Zs, 2 times of Zs minus 2 times of Zm on one side plus what is equation number 2? Zs plus 2Zm, Zs plus 2 times of Zm is equals to this is multiplied with 2 means J20 plus J31, J20 plus J31, that will be J51. 2Zm will be cancelled out and 3Zs equals to J51. And how much is the value of Zs now? J51 by 3 means 17 ohms. J17 ohms. That's the value of self-impedance. And what's your answer now? Answer will be 17 ohms, you should say. 17 ohms. Okay. So we have to fill this blank with a number of 17. That's the self-impedance of each branch. Self-impedance of the each branch. Clear? Okay, next I'll take one more problem in the view of sequence network construction, as I said you. Yeah, so I'm going with next slide to take up the problem. So it looks to be a big problem, but to explain you as a whole about these positive, negative, zero sequence networks, I'm taking this one. Yeah, go through this one. Yeah. So I'll come back within 1 minute. You please read these statements what I have given. Okay. Try to understand and look at the required thing. Yeah, sorry, I'm really sorry, dear students. Okay, go this one. Consider the following single line diagram. Find the positive, comma, negative, and zero sequence Thevenin's impedance with respect to midpoint of the line P. So he said one midpoint of line P here. Yeah, midpoint of line he said P here, and you have to find the positive sequence Thevenin impedance, negative sequence, and zero sequence Thevenin impedances. Simple. Okay. So already all reactances are given in per unit form on the common base. That statement is given. So no headache, no need to consider common base and all, as we have done in case of per phase impedance diagram. Okay, let's take in the solution positive sequence network. Okay, positive sequence network. Positive sequence network. First, let us take this diagram because it will be helpful to you while you are drawing that network. Okay, so I'm showing that here. I'm taking these bus numbers, for our clarity. So bus 1, bus 2, bus 3, bus 4. 1, 2, 3, 4 buses. Okay. So it's the bus 1 I am showing. Bus 1 we are showing. At bus 1 you have generator 1, generator 2 will be in parallel, right? G1, G2 will be in parallel. How you represent G1 in the positive sequence network? A reactance or impedance with the voltage source. Represented as an impedance with voltage source. Neutral. Generator 2, impedance with a voltage source again. Impedance with a voltage source. And it's a neutral. And this is positive sequence impedance of first generator. ZG1 of generator 1. Notations only. Don't bother. If you know numbers, you write numbers. That's better. Even compare it to these things, you write numbers better. What is generator 1 positive sequence impedance? J0.15. Generator 2 also same number, J0.15 only. So I'll write numbers directly as I said you, 0.15 per unit, here also 0.15 per unit. Bus 1 to bus 2, we have a transformer. Bus 1 to bus 2, we have a transformer. The transformer will have positive sequence impedance of 0.1. It is represented as a series impedance. Bus 2 transformer, it is J0.1. Next thing, bus 2 to bus 3, have a line. You cut that line into two equal parts. And half reactance positive and half reactance positive we should keep here. So this is point P here. And okay, so it's a bus 3. And half of the line reactance positive sequence means 0.05 by 2. And remaining half we should keep here, 0.05 by 2. And bus 3 to bus 4, we have a transformer. You keep the transformer as series impedance model J0.1. Bus 3 to bus 4, you have to keep transformer as a series impedance model. How much is that? J0.1. Okay, J0.1. Okay, at bus 4 you have a motor. How you represent motor? Motor representation will be similar to generator. So we have to keep that in this way. Okay, so it's plus, minus, and you have to keep positive sequence impedance of motor. What's the positive sequence impedance of motor? J0.05 given in the data. J0.05 given in the data. Okay, don't bother about these voltages. Don't bother about those voltage values. Our aim is to find out positive sequence Thevenin impedance with respect to point P, so called midpoint of transmission line. Now, in the next diagram, I will draw by killing the sources. You observe 0.15 will be in parallel. That will be in series with 0.1. In series with this. That network analysis we have to do further. Okay, let's copy this. So I'll write in the next slide by killing the sources. By killing the sources. Okay, so I am I'm giving that here. This one. I have to kill this source. These sources we should kill. Okay. So by killing these sources, in the sense, you'll get a short here like this. Okay. And this J 0.05 by 2 means it is J 0.025. We can write this number is J 0.025. 025. So with respect to point P, we have to find with respect to point P. 0.15 in parallel, it will be 0.15 by 2. So it will be J 0.075. And this is 0.1 and 0.025. Yeah, if you are comfortable, you write directly what is your resultant impedance on the left side. Okay, so it is J 0.025 and it is J 0.1. And this side is J 0.075, right? 75. And on the other side, again, J 0.025 and J 0.1. And here again, you have J 0.05. And with respect to point P, we have to get point P. So left side, what's the whole impedance you get? I think J 0.2. Right side, you get 0.025 plus 0.1 plus 0.05. Right side, you get J 0.175. So left side, it is 0.2 per unit. J 0.2 per unit. Yeah. So right side, it is J 0.175 per unit. 0.175 per unit. Now you have to get this with respect to point P. Okay. So now you write with respect to point P, positive sequence Thevenin impedance, Z1 equivalent or Z Thevenin 1, any word. It is J.2 in parallel with J 0.175. And you take the J out, you can write this 0.2 into 0.175 by 0.2 plus 0.175. Okay, you please calculate this number. So 0.2 into 0.175 by 0.2 plus 0.175. So this number is coming as 0.0933. J 0.0933 per unit. J 0.0933 per unit. This is a positive sequence Thevenin impedance with respect to point. Okay, next thing. Negative sequence Thevenin impedance. Negative sequence Thevenin. First, you draw negative sequence network. Okay, so I'm taking up the next slide. Next slide. Yeah, so negative sequence network. First, I will show that single line diagram for our understanding. I'll show that single line diagram once. This one. You don't need to draw this again and again. This you have already in your question. For easiness in understanding, I am showing that in each slide. Yeah, it's a bus one. Bus one. Left side to the bus one. Two generators in parallel. So generator 1 negative sequence impedance and generator 2 negative sequence impedance we should take. You don't get any source. Here, you don't get any source. It is generator 1 negative sequence. And it is generator 2 negative sequence. Let's take up these negative sequence impedances in the data. Again, J 0.15. Both generators are having equal negative sequence impedances. And this number was J 0.15 and this number is also J 0.15. Bus 1 to bus 2, you have a transformer. You keep that with the negative sequence impedance of transformer. How much? How much is that number? J 0.1. J 0.1. Bus 2 to bus 3, you have a line that you should divide into two parts. Because with respect to midpoint of line, we have to do that Thevenin impedance calculation. And what is the negative sequence impedance of line given? Reactance is 0.05, half on one side means J 0.025 on left side. Right side, again you get J 0.025. And then bus 3 to bus 4, you have a transformer. Bus 3 to bus 4, you have a transformer. It is represented as a series impedance, and that is again 0.1 only. If you want to check that number, T2 transformer, is same as T1 transformer. Okay, and you have a motor, it will be represented again as an impedance in this manner. Okay, so how much is that motor negative sequence impedance value? J0.05 only. From the data given, it is J0.05. And this is a point P. This is a point P. And how this negative sequence network looks to you with respect to positive sequence? Whether both networks are looking almost same? Whether both these networks are looking almost same? Yes, right? Positive sequence network and negative sequence network looks to be same. Not only that, all these impedances are equal. Whatever the positive sequence network impedance we have, negative sequence network impedances, both are exactly equal. So with respect to point P, if we calculate negative sequence Thevenin impedance, it will come same as positive sequence Thevenin impedance. Okay, yeah, I will write those conclusions now. The positive and negative sequence impedance networks, in bracket you write by killing the sources. By killing sources are looking same. This is one comment. Next comment is, when I can say positive sequence Thevenin impedance and negative sequence Thevenin impedance is equal. When I can say positive and negative sequence Thevenin impedance is equal with respect to a point, means if all the apparatus in the system are having equal values of Z1 and Z2. Then you can say Z1 equivalent and Z2 equivalents are same with respect to one particular point. Getting all of you what I said? Clear? So I will, if you check the apparatus, what you have a generator, transformer, line, and a motor. That's it. Okay. For transformer, already you know Z1 equals to Z2, right? For line also, you have Z1 equals to Z2. So especially for generator, there is a chance to have Z1 and Z2 as unequal. There is a chance to say Z1 and Z2 are unequal for generator. Means if I make a comment like this, if all the synchronous machines are having positive and negative sequence impedance as equal, then definitely Z1 equivalent and Z2 equivalent measured with respect to one particular point are equal. Okay, anyhow, doesn't matter. I will write the first statement itself here. If all apparatus in the system, has equal positive and negative sequence impedances, equal positive and negative sequence impedances, then the values of Z7 1 and Z7 2 with respect to a certain point will be equal. Means I'll write here. Therefore, with respect to point P, in the problem what we are doing actually, negative sequence Thevenin impedance value is equals to the positive sequence Thevenin impedance value. So what is the positive sequence Thevenin impedance value? J0.0933. J0.0933. Yeah, Harshvardhan, as we are in the learning stage, I have to explain all these statements to you. How I can explain these statements without taking a problem? Just if I say the statement, how many of you can understand? So my way of teaching will be explaining the things along with a problem. That's why even though you feel the problem as lengthy, you don't get these lengthy problems in the GATE examination. Okay? In the exam, they may ask only one impedance to you. May not be all the three. They will ask only positive sequence or only zero sequence they will ask. Okay, as it is the initial problem to introduce all the sequence networks, definitely I have to discuss this type of problem. Yeah. Let's move to zero sequence network now. Zero sequence network. Zero sequence network. Let's take that single line diagram. This one, single line diagram. It's a bus one. Bus one. Okay, generator one, generator two we have, right? How you represent generator one in the zero sequence? Up to neutral, we should keep ZG0. Neutral to ground, 3 times of ZL. Okay. So generator one up to neutral. Up to neutral, we should keep ZG0. What is the generator zero sequence impedance value? J0.02. J0.02 is a zero sequence impedance of the generator. But generator 1 neutral is ungrounded. Na? As generator 1 neutral is ungrounded, it will be acting as open circuit. 3 into Zn equals to infinite. Okay, generator 2, up to neutral, we should keep zero sequence impedance of generator. J0.02 only. And neutral to ground, how much impedance we have to keep? 0. 3 Zn is equals to 0. It is 3 Zn value which is equals to 0. So this is the representation of generator 1 and generator 2 in parallel. Okay, it's a bus 1. And you have bus 2. Between bus 1 and bus 2, you have transformer. First, you have to draw open diagram for that. You should identify connections of primary and secondary. Draw the open diagram like this. It is generator, so transformer 1 zero sequence impedance. How much? J0.1. J0.1 given in the data. Okay. What is the primary connection we have? What's the primary connection? Delta. Delta means you should close the shunt switch. Delta means you should close the shunt switch. Next. What is the secondary side? Star grounded, right? Star grounded means what? Series switch has to be closed with how much impedance? 3 Zn, 0. So it has to be closed with an impedance of 3 Zn, 0. That's a bus 2. Bus 2 to bus 3 line, we have to cut that into 2 parts. First part of line like this, and it's a point P, and it is second part of the line, and it is bus 3. Bus number 3. Okay. Now you take that zero sequence impedance of line, how much? J0.15, you should keep half on one side, half on the other side. You keep like this only. 0.15 by 2 here, 0.15 by 2 here. And bus 3 to bus 4, you have a transformer that you have to draw open diagram first, like this. It is bus number 4 you have. Bus number 4. Okay, yeah. So you kindly tell me, primary connection, it's a star ground, right? Primary connection, it's a star ground. Star ground in the sense we have to close a series switch. We have to close the series switch on the primary side. So I will be closing the series switch here on the primary side, and secondary side also we should close the series switch. And how much is that impedance of transformer? J0.1. J0.1. And at bus 4 you have a motor. Please kindly observe. What is the connection of motor? Connection of motor. Star ungrounded. Star ungrounded means up to neutral we should keep zero sequence impedance of motor. Neutral to ground we should keep infinite. It's ungrounded means it is infinite. How much is the zero sequence impedance of motor? What is the zero sequence impedance of motor? J0.1 we should say. This number J0.1. Now with respect to which point we have to find Thevenin equivalent impedance? Point P. With respect to point P. So now if you want to know that, we used to get many changes in the zero sequence network. Zero sequence network is not at all comparable with the positive and negative sequences. Not at all comparable with the positive and negative sequences. Right? Yeah. So now with respect to point P, if you see, now I said one method, right? You inject one current here. Inject one current. Okay? Current will see 2 paths. First path, J0.15 by 2. J0.1, closing its path. That's good. Other path you see. If the current is flowing like this and it's open, so current will not flow in the other path. Only this portion of impedance will come in the zero sequence network. Okay, so I can say that Thevenin equivalent impedance. This side it is J0.075, and here again transformer J0.1. Right side impedance is not at all effective because that is open. So with respect to point P, if you find that Z Thevenin naught with respect to the point P, Thevenin equivalent impedance, zero sequence will be J0.175 per unit. J0.175 per unit. Okay. So I think all of you getting this one. Good. Zero sequence Thevenin impedance. Okay. Next, listen here. What is the purpose of these Thevenin impedances calculation and all? Or sequence networks construction and all, as we said here, to do some unbalanced system analysis. That also I will tell a little bit now. You see, Thevenin equivalent circuit means Thevenin equivalent circuit. Thevenin equivalent circuit means we have to find two things, right? One, Thevenin voltage. Next one, Thevenin impedance. But we concentrated till now about the Thevenin impedances calculation only. What will be the Thevenin voltage at point P? What will be the Thevenin voltage at the point P? That we have to discuss. Okay, listen please. Listen please. Listen. See, actually, yeah. Sorry. I'll copy that single line diagram that given in the question. Point P we have to highlight, as you said now. Showing in the next slide. Listen to this. See, actually, he is asking us to construct or know the positive and negative sequence Thevenin impedances and zero sequence with respect to point P. Means he may be keeping, or in future or in as a next step, he may be attempting to keep some load at the point P. He may be attempting to keep some load at the point P. Before keeping that load, you have to be ready with the positive, negative, and zero sequence Thevenin networks. Okay, I am asking a basic question to you. Whether you construct the Thevenin networks before keeping the load or after keeping the load. Whether you construct the Thevenin equivalent networks before keeping the load or after keeping the load. Tell me please. Before keeping the load or before keeping the load. So you no need to bother what he is going to keep at P now. You no need to bother what he is going to keep at P. We have to take the network as it is and we should find out the positive, negative, and zero sequence Thevenin equivalent networks. Now, whatever the voltage you have at the point P before keeping the load, whatever the voltage you have at the point P before keeping the load, that itself is a Thevenin voltage. That itself is a Thevenin voltage for you in the circuit. Will you believe it? Tell me please. Will you believe that or not? Yes. Before keeping anything, whatever the voltage you have at the point P, that itself is a Thevenin voltage. But we are dealing with a three-phase system now. Three-phase system. So I will have phase A voltage, phase B voltage, phase C voltage. Okay. So now in the previous slide, I am writing at point P, voltages, phase voltages at point P are assumed as balanced. That's our assumption actually. Because by this point of Z Thevenin naught, our problem was over. Now I am extending it to get more clarity about the calculations. So phase voltages at point P are assumed as balanced. Okay, are assumed as balanced. So I can say let phase A voltage at the point P, I am using a notation E. As E. Some magnitude at an angle 0. B. Some magnitude at an angle of minus 120 degree. C. Some magnitude at an angle of 120 degrees. Okay, now these are ABC voltages, right? But we want to know the sequence voltages because we are going with the sequence networks. So if you convert these ABC voltages into symmetrical components, what will happen to positive sequence voltage? Anybody please tell me? What will happen to positive sequence voltage? That will be same as EA, right? Which is nothing but mod E at an angle 0. That's it. Mod E at an angle 0. What will happen to negative sequence voltage? Negative sequence voltage EA to how much? It will come to be 0. And what's the zero sequence voltage? Also 0. These are nothing but Thevenin voltages at the point P. Positive sequence Thevenin voltage, negative sequence Thevenin voltage, zero sequence Thevenin voltage we should call. These are nothing but Thevenin voltages at P. Thevenin voltages at that point P. Thevenin voltages at that point P. Okay. Now I will draw positive sequence Thevenin network, negative sequence Thevenin network, and zero sequence Thevenin network. Simple, simple. So please complete it. I will move to next slide. Yeah, Vinita, I don't have any information about it. If it is there, I will tell you. Okay, Vinita? Yeah. Listen here. First, positive sequence Thevenin network. Positive sequence Thevenin network. So this is positive sequence Thevenin impedance, ZTH1. And we have positive sequence Thevenin voltage, EA1, neutral. Is a positive sequence Thevenin network. With respect to what point we have done? Point P. This is a point P. Means the total positive sequence network you have, that I have converted into a single voltage source in series with the impedance. With respect to point P. Okay. What is this Z Thevenin one? We have done this number already. J0.0933. Next one. Negative sequence Thevenin network. Negative sequence Thevenin network. This is a point P. Okay. And you don't have any negative sequence voltage source. You get only negative sequence Thevenin impedance. EA2 number will be 0 and this is a neutral. EA2 number will be 0. Just how I said that also. And it is J0.0933. 0933. Okay. Next. Zero sequence Thevenin network. Zero sequence Thevenin network with respect to the point P. Point P. You get ZTH naught. And you don't get any voltage source in the zero sequence. Ground symbol. And this is EA naught value, which is 0. And this zero sequence impedance is J0.175. J0.175. Sir, question they given phase voltage. Well, they have not given, Mohana. They have not given. We have assumed it. We have assumed the voltages before making anything at point P are balanced. Based on that assumption, you get only positive sequence Thevenin voltage. I don't have any negative sequence Thevenin voltage and zero sequence Thevenin voltage. For example, if the voltages at the point P are also unbalanced, if the voltages at point P are unbalanced, then you may get positive sequence Thevenin voltage and you may get negative sequence Thevenin voltage. You may get the zero sequence Thevenin voltage also. All the three Thevenin voltages you are going to get if you have voltages at the point P as unbalanced voltages. Okay. Yeah. So this is the end of this question. We have learned something from this question, which will be helpful to understand the further topics. Okay, let us target on the calculations of Thevenin impedance only. We'll do some problems quickly about these sequence impedances. Let's move to the next slide to take up the next question. Going to take up the next question. Yeah. The next one. Go through it. Only two I have asked, positive and zero sequence I have asked. Single line diagram. Go through this question. Already we have that in your PDF also. Read that question once. Find positive comma zero sequence Thevenin reactances with respect to bus 2. It's a bus 2. Bus 2. In the following single line diagram, all the reactances are given in per unit form on the common base. Generator x1 0.1, x0 0.04. T1, T2 both are identical. Identical in the sense in the way of reactances. May not be in connection. Okay. X1, x0 both are equal 0.1. Line, transmission line, x0 value 0.1, sorry, x1 value 0.1, x0 value 0.25. Okay. Draw positive sequence network quickly. Draw positive sequence network of this one. Nothing mentioned regarding base value. Of course, he said common base. Okay, no issue with that, I think. The solution I am saying, first I am taking positive sequence network quickly. Positive sequence network quickly. First, let's copy this figure again, this single line diagram. No need to draw this again in your notes. Just for easiness in the explanation, I have taken up that. Bus 1 is this, bus 1. What do you have at bus 1? I have shown only one generator. So I will show that generator as a voltage source in series with the impedance, and it is neutral. Okay, what is generator positive sequence impedance? J0.1. J0.1, and we have some voltage source here. Bus 1 to bus 2, we have two transformers in parallel. Bus 1 to bus 2, two transformers in parallel. First transformer, second transformer, represented simple as series impedances, as you know. What is first transformer series impedance? Sorry, positive sequence, J0.1. Second one is also having equal impedance as 0.1. Next, we have a line. How that line is going to be represented? It will be a series impedance. How much is positive sequence? 0.1 reactance, J0.1 per unit impedance. And this is neutral. How we will represent infinite bus in the positive sequence network? Anybody? How we will represent? How you will represent that infinite bus in the positive sequence network? Gokul Shyam, that unbalance may happen due to unbalanced voltage and current flow because of load. Gokul Shyam. How you represent this voltage source? It's a generator. Infinite bus means you treat that as a generator or synchronous machine. Synchronous machine with zero impedance. Infinite bus, you treat it as synchronous machine with zero impedance. Means in the positive sequence, it will be represented as a generator, sorry, voltage source. Voltage source. Now, in the next step, by killing the sources means we can move these sources away. Okay. And you have to find your Thevenin impedance with respect to bus 2. So with respect to bus 2, if you redraw this model, it's a bus 2. Left side, you take 0.1 in parallel with 0.1, 0.05. That in series with 0.1 means this side you are going to get J0.15. Left side you get J0.15. And right side you get J0.1. Right side you are going to get J0.1. And with respect to bus 2, if you find that Thevenin impedance, J0.15 in parallel with J0.1. That's a Z1 equivalent. Okay. So with respect to bus 2, positive sequence Thevenin impedance will be parallel combination of J0.15 and J0.1. So you can take that J out and you can write that number only. So you can get this value. How much? 0.15 into 0.1 by 0.25. It will come J0.06 per unit. J0.06 per unit. J 0.06 per unit. Yeah, so I'm sorry, by mistake I kept cross mark here, it's plus. J 0.06 per unit. Okay, next. Negative sequence network will draw and we'll find out the Z0 equivalent with respect to bus 2. Yeah, I will move to next slide to take up zero sequence network. Sir, for delta transformer, don't give connection to reference. As I can already, it's a positive sequence network, right? You no need to bother about connections of transformers, winding connections of transformers. Yes or no? So zero sequence network, I will show network like this, single line diagram. Okay. It's a bus one, you take bus one. First, generator. In the zero sequence, generator is going to be represented in this manner. Up to neutral, we should keep zero sequence impedance of generator. Neutral to ground, we should keep 3 times of ZL. As that is solidly grounded, as it is solidly grounded, we should keep this as 0. Keep that as 0. Okay. How much is zero sequence impedance of generator? What is zero sequence impedance of generator? J 0.04 given in the data. J 0.04 given in the data. Okay. Next, bus 1 to bus 2, you have many things to show here. Bus 1 to bus 2, we have many things to show. You have to be clear now. So bus 2. Bus 1, bus 2. Upper transformer, open diagram. Upper transformer, open diagram. What is that impedance? Zero sequence impedance of transformer? J 0.1. Okay. Primary side, what connection? Delta, shunt switch close. Secondary side, star ground, series switch close. Primary side, delta, shunt switch close. Secondary side, star ground, series switch close. Next one. Second transformer, open diagram I have drawn like this. And this transformer impedance also J.1 only. J.1 only. What is primary connection? Star solid ground means primary series which will be closed with zero impedance. Secondary side also star solid ground only. Series impedance is closed with zero impedance. That's it. From bus 2 to bus 3 means infinite bus. We have a line. Line means it will be represented with its zero sequence impedance. What is zero sequence impedance of line? J 0.25. J 0.25. How you have to represent this infinite bus in the zero sequence network? Anybody please tell me? Anybody please tell me how you represent infinite bus in the zero sequence network? Short circuit. Why? It's a generator with zero impedance. Nah? If it's a generator with zero impedance means it will act as a short circuit. Okay, so in the positive sequence network, listen to me. In the positive sequence network, infinite bus is represented as a voltage source. In the negative sequence network, it is represented as a short circuit. In the zero sequence also, it will be represented as a short circuit. To tell about that, I have taken up this question. Okay, yeah. So I will be showing that infinite bus as zero impedance. Zero impedance. Now, with respect to bus 2, we have to calculate that zero sequence Thevenin impedance. Just if you redraw this network, 2 to ground J 0.25. Again 2 to ground J 0.1. 2 to ground J 0.1. And then 2 to ground in this way J 0.14. Clear? Okay. I'll redraw this. Next slide I will take. Next slide. So it's a bus 2. Left side, first left side J 0.14, transformer 2, generator. Transformer 2 and then generator J 0.14. J 0.14, one number. Next, transformer 1 impedance directly connected to ground, that is J 0.1. J 0.1. Okay, of course, it's a ground terminal. Next, after that, 2 to ground, you have J 0.25. J0.25. Okay, now we have to get the equivalent impedance with respect to this terminal. Na? So with respect to bus 2, Z0 equivalent value is equals to Z0 equivalent value will be equals to how much is that? Okay, you take up your own calculation. I'm writing like this: 1 by 0.14, 1 by 0.1, 1 by 0.25. It is one of the easiest way of doing the calculation. It is one of the easiest way of doing the calculation if you have three numbers, right? So 1 by 0.14 plus 1 by 0.1, 1 by 0.25. You have to find inverse of this. It will be J0.0473. J0.0473 per unit. J0.0473 per unit. Okay. Two transformers only. What's the doubt you have, Sri Divya? So what's there in that Mona? It will be simply replacing each and every apparatus with its zero sequence network. Generator, up to neutral, you should keep zero sequence impedance. Neutral to ground, 3ZN. Transformer, we have discussed yesterday also. How to represent if it's a primary and secondary. What about that impedance? What is that impedance, Sridivya? What is that impedance, Sridivya? Yeah, Harshavardhan, whichever the way you are comfortable, you calculate the parallel combination of three impedances. Z0 equivalent J0.14 in parallel with J0.1 in parallel with J0.25. You calculate according to your view. Whatever your view have, according to that, you calculate the parallel combination of the three. Some people will say first they will take J0.1 representing second transformer, correct? Yeah, infinite bus bar, listen, I have discussed yesterday also, maybe in previous class, may not be yesterday. Represented as voltage source, ideal voltage source, right? Ideal voltage source means positive sequence impedance is 0, negative sequence impedance is 0, zero sequence impedance is also equals to 0. But in the positive sequence, you have a voltage source with Z1. Voltage source will be there. Z1 is 0. And negative sequence, you don't have any voltage source. It will be simply shorted. And zero sequence, you don't have a voltage source. Simply it will be shorted. Okay. So positive sequence network of infinite bus. Positive sequence network of infinite bus. It will be simply voltage source. Z1 equals to 0. Negative sequence network of infinite bus. Z2 equals to 0. So it will be shown as simply a short circuit. Z2 equals to 0, no voltage source. Whereas in the zero sequence network of infinite bus, it will be represented again with the short circuit. Z0 is equals to 0, no voltage source. That's it. Need to have in parallel be connected. Oscar, it's ground, right? It's a ground. It's a ground. Just move this point 1 from point 2 to ground. Ground is nothing but this point. You join these two if you want. Bhaskar, it's a ground, nah? It's also ground, right? You join these two if you want. It will come. Okay. Done. Next, one more question I want to ask you. One more question in the same problem. Calculate the zero sequence Thevenin impedance with respect to bus 1 in per unit form. Okay, same question as previous. I will repeat. Same as the previous question. Same data of previous question. Find zero sequence Thevenin impedance with respect to bus 1. With respect to bus 1. Anybody? Can you tell the answer for this? With respect to bus 1? Already zero sequence network is available. Just to take up that network directly. This one only. This is a zero sequence network of that single line diagram you have drawn already. Okay. See, you have to find out that zero sequence impedance with respect to bus 1. Na? So with respect to bus 1, you have to find bus 1. Anyway, it is grounded. See, now if you redraw this, I have to remove this. It will confuse me actually. It's already grounded as we have shown. Already grounded. Now you see, 0.2 to ground, you have J0.25. Again, 0.2 to ground, you have 0.1. Na? So this 0.1 and 0.25 will be in parallel. It's a ground terminal. Now you join this ground, for your clarity only I am drawing this. You join this ground point to this one. Okay, now 0.1, 0.25 will come in parallel. That will come in series with 0.1. Okay, that whole number will be in parallel with 0.04. Whole number will be in parallel with 0.04. It's simple network analysis only. Basic network analysis. Okay, Vinita, it is J0.04 for generator. Then what I have to do with that? Tell me, please. J0.04 only, Vinita. What's the problem with that? That 0.04 is connected in series with 0.1. In series with 0.1. Okay, let me draw in the next slide. Next slide. It's a bus 1. Bus 1 to ground, you have J0.04. J0.04. It's a ground terminal. Okay. Next thing you see, bus 1 to bus 2, you have J0.1. Bus 1 to bus 2, you have J0.1. Okay. Next one. Bus 2 to ground, J0.25. Bus 2 to ground, J0.25. Not only that, again bus 2 to ground, you have J0.1. That's a transformer 1 impedance. Again bus 2 to ground, you have J0.1 per unit impedance. Okay. Now, with respect to bus 2, we have to find out, bus 1, we have to find out the equivalent Thevenin impedance. Yeah. So now you can redraw this 0.25 in parallel with 0.1. That will be in series with 0.1. So 0.25 in parallel with 0.1. It will be 0.0714. This parallel combination. This parallel combination is J0.25 into J0.1 by J0.25 plus J0.1. So it will be J0.07143 per unit. That is in series with 0.1. So I will show this diagram. So I have to show in the next slide, else I'll try to adjust here. 1. This side you have J0.04. Other side you have J0.17143. 17143. Now you can say Z0 equivalent with respect to bus 1, J0.04 into J0.17143 by J0.04 plus J0.17143. 17143. Get this number? J, how much? Anybody? So this is 0.0324, J0.0324 per unit. That is a zero sequence Thevenin impedance with respect to bus number 1. Bus number 1. Yeah. So all of you getting this? Fine. So have a break. After break, we discuss 2 more problems in this sequence networks, particularly zero sequence network I will discuss. Then we will move to the fault analysis. Anyway, I will display the question what we are going to discuss after break. So I am showing that question to you. Yeah. So go through this question. This is a question what I am going to discuss immediately after the break. 15 minutes break. 15 minutes. So I have resumed the audio video on screen. Kindly observe. Yeah. So let's continue with this question, what I displayed on this slide. Consider the following single line diagram, which consists a generator and a transformer with their zero sequence reactances given in the figure. Generator zero sequence reactance is 0.1, transformer 0.2. Okay. The zero sequence Thevenin impedances measured with respect to generator terminals. Generator terminals means this bus bar. With generator neutral isolated. Generator neutral isolated means neutral not connected to ground. And with neutral grounding impedance of 0.05 plus J0.01 or Z01 and Z02 respectively. The ratio between Z01 and Z02 is dash. In bracket, he is asking only magnitude. Okay, yeah. So let's think about this question first. Solution. First, let us copy this diagram, this single line diagram. Single line diagram like this we have. See, actually, he is saying zero sequence impedance measured with respect to terminals of the alternator, maybe this point. With respect to this point, we have to measure the zero sequence impedance. First, if the alternator neutral is ungrounded, means isolated neutral, he said that zero sequence impedance is Z01, some value that we have to calculate in fact. And if that neutral is grounded, after grounding that neutral, zero sequence impedance is Z02. And he is asking what is the ratio between the Z01 and the Z02. Okay, first I'll say without neutral grounding, first to draw the zero sequence network here. First to draw the zero sequence network without neutral grounding. It's a generator terminal with respect to what we have to find. Generator, how you represent? Up to neutral zero sequence impedance of generator. Okay. Neutral to ground, what we should keep? It's isolated neutral, na? 3 times of Zn means that will be infinite. Open. Okay, it's a generator terminal. Okay. And from this generator bus to other, we have a transformer. Now we have to think about the transformer equivalent circuit. Which diagram we are drawing? Zero sequence diagram, na? So I have to identify what the primary connection, secondary connection. We should give the series switch and shunt switches and all. So let's show first open diagram. Zero sequence reactance of transformer 0.2 means impedance will be J0 point. Primary what connection? Star ground means series switch close. Secondary what connection? Delta shunt switch close. Okay, and the other side of this transformer we have a open. Okay, that you can leave simply. Now, with respect to this bus, so-called the generator terminals, what is the zero sequence Thevenin impedance value? With respect to generator terminals, what will be the zero sequence Thevenin impedance value? How much? Anybody tell me? 0. J0.2. That's it. J0.2. Okay. So with respect to generator terminals, zero sequence Thevenin impedance, Z Thevenin naught, that they have symbolized as Z01. Z01 in the question is equals to J0.2 per unit. Next case, I'll say with neutral grounding. So next slide I am taking with neutral grounding for generator. How much is that neutral grounding impedance is said in the problem? 0.05 plus J0.01 per unit. 0.05 plus J0.01 per unit. Now, just you can draw that same diagram as it is. Same what we call zero sequence per phase model as it is. But only one change is that for generator neutral to ground, we should keep that 3 times of Z. between the generator, neutral and ground, we should keep 3 times of Zn. How much is that 3 times of Zn? 0.15 plus J 0.03. 0.15 plus J 0.03. Okay. Now, this J 0.1 and this number is in series. So left side are right directly with respect to generator terminals. Thevenin equivalent impedance, zero sequence, or Z02 is equals to parallel combination of J.1 plus 0.15 plus J 0.03 one side, right? In parallel with J 0.2. Okay. Yeah. So now I will write that Z02 in the next slide. Z02 in the next slide. Else here, if you write in simplified way, 0.15 plus J 0.13 that in parallel with J 0.2. J 0.2. I'll take in the next slide and I will try to rewrite that in a simplified way finally. So I'll take next slide. Z02 is equals to 0.15 plus J 0.13 multiplied with J 0.2 by summation of the two impedances. You should take 0.15 plus J 0.13 and 2, that will be 33. Like this. Okay, you keep as it is. Now, what is asking? Ratio between Z01 and Z02. Ratio between Z01 and Z02 is asking. What is Z01 number? J.2 whole by Z02 number 0.15 plus J 0.13 into J.2. This by you get 0.15 plus J 0.33. So that J.2 will be cancelled out. We'll get 0.15 plus J 0.33 whole by 0.15 plus J 0.13. Like this, you will get that result. You need only magnitude, right? Magnitude. Magnitude means magnitude of numerator by magnitude of denominator. That's it. Modulus of Z01 by Z02 means we have to take numerator magnitude 0.15 square plus 0.33 square under root. Denominator magnitude square root of 0.15 square plus 0.13 square. Okay, get this number how much? In virtual calculator, it is possible to take that. Jadan already have taken 3 times. And what's your doubt, Mukesh? Jadan already have taken 3 times, I think. Yes. So 0.15 square this magnitude will be 1.8267. 1.8262. No units. 1.8262 you can get. Yeah. 1.8262. That's the ratio between Z01 and Z02 magnitudes. Right? We'll take one more problem quickly. The zero sequence. So that's why sometimes in the exam they used to give resistances also in the network. So don't forget to write J. Don't forget to write J symbol in the reactances. Yeah. So let's take in the next slide. Next question I'm taking. It's a previous gate examination question I'm taking. Yeah, go through this question once. Previous gate examination question. Okay. A generator is connected to a transformer which feeds another transformer through a short feeder. The zero sequence impedance values are expressed in per unit on common base and are indicated in the figure. Okay. The Thevenin equivalent zero sequence impedance at point B is, with respect to point B, we have to know what is the zero sequence Thevenin impedance of the system. How much? How much? Yes, let's copy this single line diagram what they have given. I have to find zero sequence Thevenin impedance with respect to point B. Na? So solution, it was single line diagram. So just draw that zero sequence network quickly. It's a generator terminal. Generator zero sequence reactance is 0.03, means impedance is J0.03. This is up to neutral. Neutral to ground, we should take 3 times of Zn, means it will be 3 times of that resistance. 0.75 will come. Okay, so this number is 0.75 real number. Okay, so next we have a transformer of delta star solid ground. I will keep open diagram first. This impedance is J0.1. Primary what connection? Delta. Delta means what? Shunt switch has to be closed here. Secondary, it is star solid grounding. So series switch has to be closed with 0. Next, you have a line with zero sequence impedance of J0.05. Reactance is 0.05, means impedance is J0.05. So this is J0.05 per unit. After that, we have a transformer. Let's take the open diagram of transformer first, like this. And impedance of transformer is J0.07. Impedance of transformer is J0.07. Primary what connection? Star solid ground, series switch close. Secondary what connection? Star with some resistance ground. So we have to close this series switch with 3 times of Zn, means 0.75 per unit. And this is the point B, what he is asking us to concentrate. Point B. Now with respect to point B, we have to find out Z0 equivalent. With respect to point B, we have to find Z0 equivalent. All are in series. What is the total impedance? 0.75 resistance plus J0.07, J0.105, J0.1. So with respect to the point B, Z0 equivalent value, resistance is 0.75 and plus J, reactance is J0.22, like this you will get in per unit domain. 0.75 plus J0.22. What's the answer given? Option is B. Correct option is B from ABCD given. Option is B. 0.25 means it is a resistor, right? 0.25 means it is a resistor. He has shown resistance symbol here. Resistance symbol he has shown here. So we should take 0.75 resistor. 3 into Zn. 3 into Zn. Okay. So I'm showing the question slide. Question slide. It is there in your power system CRO. That classroom objective questions you have one file, right? In that one, it is there, that question. Yeah, next. One more question I'm taking up. One more question. See this. Consider the following single line diagram in which the apparatus names are mentioned. Names of the apparatus are mentioned as, see that, G1, G2, G3, T1, T2, M, line 1, line 2. Look at the diagram. Look at the diagram. G1, G2, T1, line 1, line 2, T2, M, motor, G3. Assume that the system is at no load condition. 1, 2, 3, 4, 5 bus numbers. 1, 2, 3, 4, 5 are bus numbers. Okay. One, two, three, four, 5 are bus numbers. Now the question, actual question I have to give here. Actual question is this. If a three-phase zero sequence current, is injected at bus 2, then which of the following apparatus will carry zero sequence currents? Which of the following these apparatus will carry zero sequence currents? If you are injecting zero sequence current at the bus number 2, okay, it's a variety of question. Till now we didn't face this type of question in the examination. We didn't face in the examination, expecting to get maybe in GATE exam further. Okay, yeah, listen here. See, to know which apparatus are carrying zero sequence current, by injecting that current at one place, simply draw zero sequence network of that. Whatever the single line diagram, yeah, for that you draw the zero sequence network and you inject some current at bus 2. See, once after drawing zero sequence network, whatever the current you inject is obviously zero sequence current. And after injecting some current at bus 2, check how that current is passing, how that current is closing its path. Thereby, you can confirm which apparatus will carry that current, which apparatus will not carry that current. Okay? Yeah. Anybody said the answer already? Okay, so let's move to the solution now. I have to go with the next slide to give the solution, because I have to draw the zero sequence network. First, let's copy that single line diagram. For the sake of reference, I am copying this one, such that I can identify easily what is that type of each and every equipment. Okay, so it's a bus 1. Bus number 1. First, bus 1, you have G1, G2, 2 generators, both are solidly grounded. Generator 1, grounded like this. Generator 2, neutral, grounded like this. Okay, let's call this name. It is G1 and it is G2. Leave it. No need to bother about impedances. G1, G2, I would say. Bus 1 to bus 2. We have a transformer. I should show open diagram first for the transformer 1 P1. Okay, what's the primary connection? Primary connection, it is delta. Delta means you have to close a shunt switch like this to the ground. And secondary, it is a star solid ground, this series switch will be closed like that. Bus 2 to bus 3, you have a line. Bus 2 to bus 3, you have a line. I will call it is line 1. It's bus 3. Line 1. And at bus 3, what you have? Motor. Motor means up to neutral, we should keep that zero sequence impedance of motor. Neutral to ground, it is shorted. 0. So it's a motor. Symbol M. Motor. Next one. At bus 2, we have a line 2. Let's tap this. Line 2. And this is a bus number 4 actually. Bus number 4. At bus 4, what you have? You have a transformer of star ground. First to draw open diagram for this T2 transformer. Okay, star ground means primary series switch close, secondary also series switch close. Next, you have a generator star ungrounded. Means up to neutral, we should keep generator impedance. Neutral to ground, it will be open. Neutral to ground, it will be open. Neutral to ground, it will be open. Okay, see, actually, this point is ground. This point is ground. This point is ground. This point is also ground. So you can join all these ground points together. No issue. You can join all these ground points together like this. This is a zero sequence equivalent network per phase. zero sequence equivalent network per phase. Now listen here, listen. In this network, you have to inject some current at bus number 2. You have to inject some current at bus number 2. So what you have to do actually is, you keep one current source at bus 2. You keep one current source at bus 2. That itself is a zero sequence current, because a network is a zero sequence network. See, after injecting this current will see three paths. One path through T1 closed. So T1 will carry zero sequence current. T1 will carry zero sequence current. And this current is flowing through line 1, motor, closing. So line 1 will carry, motor will also will carry the zero sequence current. And whatever the current we are saying now, that will flow through line 2, T2, G3. But you have open, right? Open means this branch will not carry any current. This branch will not carry any current. Means which apparatus are carrying this zero sequence current? T1, line 1, motor. Means with respect to bus number 2, if you talk, only T1, line 1, motor will carry the zero sequence currents. Okay, right. So with respect to bus number 2, T1, line 1, comma motor will carry zero sequence currents. Will carry zero sequence currents. Yeah. So all of you getting this one? So what's your answer? C. C is a correct answer to be chosen. C is a correct answer to be chosen. Okay, I will ask one simple question to you. Just tell me your answer in your view. Simple question only. Star grounded generator. Don't think about this problem. Forget about this problem. Star grounded generator. Will it carry zero sequence current or not? Forget about this problem. Just give me the answer. Star grounded generator. Will it carry zero sequence current or not? Yes, definitely. Yes. But if you enter into the power network, is it going to carry zero sequence current or not? It depends upon the remaining equipment in the system also. Remaining apparatus in the system also. For example, you see in this diagram, generator 1, generator 2, both are solidly grounded, but still these are not carrying the current. Why? In the sense, we are having a disturbance at bus 2. That zero sequence current is not at all entering into G1 and G2. All of you getting my point? Okay? Yeah. Next thing. Very simple question. Delta star ground transformer. Else you take up star ground. Better one. Star ground. Will it carry zero sequence current or not? What's your answer? You have to say. Star ground. Will it carry zero sequence current or not? Yes, you should say. You should say it is. Yes. Star ground will carry zero sequence current. But after entering into the network, is it going to carry or not? It depends upon the other equipment in the system also. For example, in this particular case, even though this transformer is allowing closed path for zero sequence current, but generator 3 is not supporting. By making this one open. So in that perspective, transformer 2 may not carry the zero sequence current, even though it is star ground. All of you getting? Depending on the network. See, if he is asking only one equipment, you just look at the equipment and tell the answer. But if he is asking that equipment in the network, you should look at the whole network and you should say, is it going to carry it or not? Okay, same question. I am repeating with some different requirements here. Just look at this one. In the previous problem, in the figure shown in the previous problem, if zero sequence current, 3-phase zero sequence currents are injected at bus 5, then which apparatus will carry that current? Anybody please tell me the answer for this? Yeah. See, if you are injecting, this is a bus 5, right? This is a bus 5. So if you are injecting current at bus 5, G3 will not carry because it's open, but that current will flow in T2 line 2. T2 line 2. Then it will divide into two parts. T1 will close. Line 1 motor also closes. Getting all of you? Yes, right. Except generators G1, G2, G3, all apparatus will carry. Of course, your answer is B for this. Answer for this problem is B. Just go through it. Just go through it if you have any doubt. So by this point, we finished the what we call sequence networks construction and all. This is sufficient with respect to your examinations, GATE or ESE prelims. A generator, at generation, do we have grounded generator? Definitely, Ashish. Definitely. The generator will be always neutral grounded. Star, moreover, it is neutral grounded. Neutral grounded. Okay. So I'm closing this file. I am opening a new file in the view of the fault analysis from this point. Symmetrical and asymmetrical fault analysis. Throughout means its path will be through ground. Correct. Correct, Rakesh. Correct. Line 2 will also carry, right? Motor M is having a closed path. Line 2. No, line 2 will carry. Why it is so means you are injecting current here, right? You are injecting current at bus 5 means it will flow through T2 and line 2. T2 and line 2. Yeah. Some basic introduction, I am going to take up the fault analysis. The fault analysis. In question, did he gave to inject? Yeah, yes. Sai Charan Reddy. If I am discussing the questions, just please open the PDF file what I have uploaded to you. Okay, there is a purpose why I have uploaded. Whenever I am discussing the question, I may move off. I may not wait for a long amount of time to note down the question in your book. Okay, so you have that PDF file. Get a printout of that. Keep it with you. Whenever I display the question, just match that question in that particular chapter and be clear about that question first while I am reading. Okay. So this is our next chapter, as I said you, symmetrical and asymmetrical fault analysis. Little introduction thing we are going to discuss here. First of all, sir, this faults in the power system network are abnormal conditions. I will say in two ways. Two types of faults you can say in the system. One, short circuit fault in the system. Second one is a open conductor fault or open circuit fault. Okay, yeah. So two types of short circuit faults exist in the system. Types of short circuit faults. Types of faults. I'm really sorry. Types of faults. It will be of two types. We are saying. First one we are calling short circuit fault. Short circuit faults. Second one we are calling open conductor faults. Open conductor, or you can say open circuit faults. Open conductor faults are open circuit faults. Open conductor or open circuit faults. See, sometimes these short circuit faults can also be called as shunt faults in the system. Parallel shunt faults occurs in shunt with the system. Okay, so shunt faults, we will call these things shunt faults, and these faults are going to be called as series faults in the system. series faults in the system. Okay, first I will be discussing about what are the consequences of getting short circuit fault in the system. Right? What are the various disadvantages we are going to face with respect to short circuit faults in the system? After that, we will see what are the consequences of open conductor faults. After discussing about these two, my interest is to continue this only with respect to short circuit faults in the system, particularly with respect to the examination point of view. Okay, yeah. First heading I'm going to take consequences of short circuit faults in the system. Consequences of short circuit faults in the system or shunt faults in the system. Okay, to explain you this in a more clear way, I am taking a single phase system here. Single phase system. Okay, single phase system I am taking to explain you this one more clearly. It is a single phase generator. One terminal is grounded. For this generator, one terminal is grounded. And it's connected to one line, transmission line wire, something like this. At the end of this line, we have some load. At the end of that line, we have some load. Please kindly cross-check your question, Mr. Anonymous attendee. Series faults means occurring in series with the conductor opening. Okay. Listen here. So this is a line having an impedance of Z line, I will say. Load is having an impedance of Z load. Assume that generator is ideal one, does not have any internal impedance. Generator internal impedance is 0. Source voltage is Vs. How much is the current flow in this system? What is the current flow? That current itself is a load current. Whatever the current flowing in the system, that itself is a load current also, you can see. So that current I is nothing but load current only, and just based on the basic network analysis, it is source voltage Vs by line impedance plus load impedance. Line impedance plus load impedance. But generally, how is this load impedance value compared to line impedance? How is the load impedance value compared to load impedance? It will be very less. Else in reverse, if you talk, load impedance number practically very, very high compared to the line impedance value. It is in the healthy operation mode. But unfortunately, if you have a short circuit fault at the load location, let us see. We are taking that fault at the load location. Practically speaking, anywhere you may have a possibility of getting fault. Anywhere you may have a possibility of getting fault. But I am taking that fault in our study at the location of load. Okay, so fault at loading. Fault at the loading means this is that fault what we are showing now, short circuit fault. Short circuit fault in the sense, simply this particular point is connected to ground. With zero impedance. See, in the way of network theory, if you want to talk, simply I can say, fault is nothing but keeping a zero impedance in shunt with the system at a particular location. But if you are saying it is not zero practically, it may be very, very low number. But I am speaking this number with 0. Okay. See, whenever it becomes 0, what will happen to this node voltage? Becomes 0. That node voltage will fall down to 0. Whenever the node voltage falling down to 0, you have a great voltage difference from sending end side to the receiving end side. How much is that voltage difference you have? Vs minus 0. And you have a Z line. Already I said Z line is very, very less. And this will carry a huge amount of current, which you use to call as fault current now. So that fault current equation, if you write, Vs minus 0 by Z line. As a Z line is very, very less compared to Z low, IF is very, very large number. You tell me first. You tell me first. In your understanding, what is the first consequence of short circuit fault in the system? What is the first consequence of short circuit fault in the system? Is it voltage falling down to 0 or current will rise? What you should say? Voltage will fall down to 0. How huge current will flow? Because of low voltage, right? Low voltage at the receiving end side. Yes or no? So the first consequence of the short circuit fault I am writing here, voltage, operating voltages in the system will fall down. Operating voltages will fall down. Or you write system experiences under voltages. System experiences under voltages. Under voltage. Okay. Next, after that statement, you have to say the system will carry heavy current. System carries heavy current, very large current, or you can write overcurrents. Overcurrent. Okay, what will happen if the system is carrying overcurrent? What will happen if the system is carrying overcurrent? And if it carries, yes, Aishwarya Venkatesh. See, if it carries very high current and that is flowing to transmission line wire, transformer in the practical system, and flowing in the generator also. And if it flows for a certain amount of time, the heat development in the apparatus exceeds a certain value. If the heat development exceeds certain value, definitely we can experience some thermal damage for that particular apparatus. Okay, so I can say heat development is high in various apparatus. Heat development is high in various apparatus. That implies apparatus experiences thermal damage. Apparatus experiences thermal damage. Okay, apparatus experiences thermal damage. Okay, that's one consequence. Next consequence I will tell you. Next consequence. See, whenever this voltage is falling down to 0, how much is the current carried by load? You can say almost close to 0. Else, rather than current, what I will say is, what is the power drawn by the load? 0. Means the load is not going to be satisfied with its requirement. Okay, so as a load is, as we are unable to supply or meet the load requirement, obviously I can say reliability of the system will be less during the short circuit fault. Okay, so I can say load is not going to be supplied. Load demand can't be supplied. So that implies you can say reliability of the system will be less. Reliability will be less for the system. Reliability will be less for the system. Okay. Next thing. Next consequence. Just this consequence. Fifth one. What I am going to say. Okay. I have to tell one more. Just listen. How much is the power factor of load you can experience generally? Generally, how much is the power factor of load or whole power factor of system in the healthy condition you can experience? Cos pi. Cos pi of the system, it may be like 0.8 lag, 0.9 lag, like that you can say. Lagging, it may be 0.8, 0.9, something like that. Okay, I'll say it's 0.9 lag in the healthy condition. But you see, after the short circuit fault has been occurred, the current to be supplied by the source is a fault current, which is Vs by Z line. And if you take this Z line, I'll write this Z line as RL plus JXL. RL plus XL, or else you write this one mod ZL at an angle of theta. Mod ZL at an angle of theta. And you assume Vs at an angle 0. Mod Vs at an angle 0 as a source voltage. Now let me rewrite this fault current. Mod Vs at an angle 0. Denominator you have mod ZL at an angle theta. So mod Vs by ZL is a magnitude of the fault current. Mod Vs by ZL is the magnitude of the fault current. And how much is the angle of that current? Minus theta. Minus theta. Getting? Mod Vs by mod ZL is a fault current magnitude and angle will be 0 minus theta. So it will be minus theta. Means obviously the source is delivering lagging current. Source is delivering lagging current. So during short circuit fault, the source power factor is lagging. How much lagging? Means it is cosine of angle between voltage and current. Means it is cos theta. Cos theta. What is theta? Impedance angle of the transmission line. Okay, I will write those statements. During fault, the power factor is lagging. Power factor of system is lagging. System is lagging. Okay, so cos theta is a power factor of system. Cos theta, a power factor equals to cos theta during short circuit fault, where theta is tan inverse of XL by RL, means impedance angle of transmission line wire. Theta equals to tan inverse of XL by RL, that is impedance angle of transmission line. But generally, that impedance angle of transmission line will be very high, practically speaking, maybe 80 degree or maybe 75 degree, like that we are going to get. Okay, so this angle is about 80 degree, I will say, about 80 degree. Now, if you take the cosine 80, cos 80, how is that number? Cos 80, very close to 0, right? Cos 80 in the sense very close to 0. Means during short circuit fault, the system power factor is lagging and it is very, very low number as compared to the pre-fault condition. Pre-fault condition means before fault occurrence. Power factor is 0.9, but after the fault has been occurred, that value was dropped down to very, very low, maybe 0.1 lag, 0.05 lag, like that we are going to get. Okay, that implies power factor of system is very low, during short circuit fault. Power factor of system is very, very low during the short circuit fault. Yeah, so all of you getting this one? Okay. Next consequence I am going to tell you. Next consequence. I'm moving to the next slide. Take up the. Yeah, is number 6. It is a bit confusions. We have different answers for this one, but I am going to explain this in one way. Just try to understand. It is one generator. And having some rotor. Just I'm showing the symbol of rotor outside. Generator, or else I'll show that rotor also inside that generator block only. So it was a generator showing that rotor something like this. And we have 3 wires coming out. Phase A, phase B, phase C wires. Phase A, phase B, phase C wires. You know, we are connecting some prime mover to the rotor. Maybe a turbine, steam turbine or hydro turbine, we are connecting to this rotor. According to that, this rotor is rotating. In certain direction, maybe like this. With the help of prime mover torque, TPM. Rotor is rotating in that particular direction with the help of a prime mover torque, TPM. Prime mover torque. And initially, I am saying the no load operation. No load operation means there is no current flow in the outgoing terminals, definitely. No current flow in the outgoing terminals. So if you don't have any stator current, if you don't have any stator current, what is the electromagnetic torque produced? Zero. Because electromagnetic torque is proportional to rotor flux into armature current. Rotor flux into armature current. Rotor flux is there. Armature current is zero. So electromagnetic torque will not exist right now. Okay, no load. Armature current equals to zero. That implies electromagnetic torque value will be equals to zero. Okay, but still we have a prime mover torque with effect of that. It is rotating with a constant speed. With a constant speed. That's it. Not only that, the frequency of the induced EMF in the stator with effect of that rotor rotation is F. Okay, frequency of induced EMF is equals to F. Frequency of the induced EMF is equals to F. Okay, so same circuit we are copying. Same circuit we are copying here. Just listen now. Now, I had a sudden short circuit on the alternator terminals. Sudden short circuit occurred on the alternator terminals. Means all of a sudden, it has moved its operation from no load condition to some loaded condition, we will say. Because some current will flow in the stator, right? Definitely, we have some current flow in the stator, something like this. IA, IB, IC. Because of this current, due to IA current, we know electromagnetic torque proportional to flux into armature current. As and when this armature current value was increasing, definitely electromagnetic torque is going to be increased. So how is the action of that electromagnetic torque? Generally, it is in opposite direction to the prime mover. Opposite direction to prime mover. So all of a sudden, I do expect some electromagnetic torque creation in the opposite direction, or some transient opposite torque was created. During the transient, some opposite torque was created. Because of that opposite torque created on the rotor, definitely rotor speed little decreases. Rotor speed little decreases. Because of that, the frequency of the induced EMF may decrease little bit. Okay, so I can say from this, that implies rotor speed expected to be reduced. That implies frequency of operation reduces. Frequency of operation reduces. Clear? Frequency of operation reduces. But I'm not saying this in the steady state operation. See, strictly if you move into stability analysis and all, during short circuit fault, we used to study. Sometimes the frequency will go high, sometimes the frequency will come down. Frequency will change continuously with respect to operating time. But as far as examination is concerned, you should remember that from this explanation what I made, you should remember that frequency of system will little fall down during the short circuit fault. Okay. So what are the major consequences we are getting due to short circuit fault? Under voltage in the system, over current in the system, low power factor of operation, low frequency of operation. These four terms we have to remember. Okay. So I'm showing in the next slide, shunt fault was characterized as or with low voltage or under voltage, better. Under voltage, comma, over current, comma, low operating power factor, and just now we are saying under frequency. Under frequency. Okay, so these are the properties of the shunt fault. Yeah. So next, let's think about that series fault, or you can say open conductor fault, series fault or open conductor fault. Here itself, I will discuss what are the different types of series faults, and then what are the consequences of the series faults at a stretch. And we'll wind up the series faults, and our continuation will be on the short circuit faults. Okay, first let me write types of open conductor faults. Types of open conductor faults. Conductor faults. types of open conductor faults. See, first of all, I will show two systems here connected by a three-phase transmission line wire. Two systems. On one side of system, we have on one side of transmission line, we have some system consisting generator, transformers, and so on. Other side of that transmission line also, we have some system consisting generators, transmission lines, and transformers. I'll show here. It is one system. System number one, I'll say. And system number two, something like this here. System number one, and this is system number two. And as a connection, we are saying just now, we have one three-phase transmission line wire. So it's a transmission line A, transmission line B, and this is transmission line C. Yeah, so these are the lines we have, ABC, transmission lines ABC, three-phase line, three-phase transmission line. Okay, next thing. Yeah, next thing. See, open conductor fault means one, I'll say any one of these three conductors got open. What is the reason means maybe because of stretch of conductor. If a contraction of conductor is more, particularly during winter seasons, that conductor may be cut down. That's one reason. Another reason, due to overcurrent flow in the conductor, that conductor has heated up and that was melted and cut into two pieces, fault. Okay, so I can say one open conductor fault is one type. Any one of the conductor was opened and the remaining two conductors are carrying their own currents. First of all, I will show in the healthy condition, IA, IB, IC, it's a healthy system first. Healthy system. So next I'll say one open conductor fault here. One open conductor fault is the first one. One open conductor fault. Yeah, so this is that three-phase system, system one and system two. So this is open. I'm making that conductor C open. Obviously, that conductor current C will become zero. Conductor C current will become zero, but remaining two conductors are carrying their own currents. So obviously, you say the system is unbalanced, right? In this condition, system will be definitely unbalanced. Okay. And the second one, you can say two conductors got open. So two open conductor fault. Two open conductor fault. Yeah. So same diagram I have copied here. Two conductors are open means maybe I will say B and C conductors was open. B and C conductors was open. So A will carry its own current. So B current will be zero. And C current also zero here. And here also the system is heavily unbalanced. For example, if the three conductors are opened, what we can say that? Can we say that as a fault? If three conductors got opened, can we say that as a fault? No, we should not say that as a fault, right? For example, if three conductors got opened, I will say that as a no load operation simply. Three conductors got opened, something like this. Then I can say all the three currents are zero. So it's a open circuit operation or no load operation we have to call, right? Right, if you want. If three conductors got opened, got opened, then it may not be treated as fault. As fault, comma, it is a no load operation. Is a no load operation. So it will be a no load operation. Yeah, good. That's it. Now consequences, first and foremost consequence, system is heavily unbalanced. System is heavily unbalanced. That is one consequence I will say. Okay, so I will move to next slide and I will wind up these consequences quickly. Some of these consequences, what I am going to write, I may explain while we move into the analysis later. Okay, first let's take this heading, consequences of open conductor fault. Consequences of open conductor fault. Okay, so first I will say system is heavily unbalanced. System is heavily unbalanced. Of course, the system will become unbalanced even for short circuit fault also. Even for short circuit fault also, system will become unbalanced. Next one. Current is less in the system because only one or two phases are carrying current, right? So low current flow in the system. Low current flow in the system. Low current flow in the system. So if you have low current flow in the system, obviously electromagnetic torque in the generator will be less. Electromagnetic torque developed in the generator will be less. If electromagnetic torque in the generator is less, then we can expect that the speed of rotor will be more. Rotor speed of generator. Rotor speed of generator will increase and operating frequency of system will also increase. Operating frequency of the system also going to be increased. Okay, rotor speed of generator is more and frequency of system is going to be increased, we can see. Next one. Because of this low current, there may be a possibility of getting over voltages in the system, right? Over voltages. Over voltages may be possible in the system. May be possible in the system. Possible in the system. Over voltages may be possible in the system. Okay, so these are some of the consequences of open conductor faults. So next, we are continuing with the short circuit fault. Immediately, what I want to tell is there are two types of faults again. Short circuit open conductor, that is one classification. You keep it aside. Keep it aside. There is another classification. Types of faults according to how much amount of time it will lie in the system. According to how much amount of time that fault will present in the system. According to it. Okay. Yeah. So I am saying here types of faults. Types of faults according to the time up to which fault will exist in the system. Fault will exist in the system. Up to which the fault will exist in the system. According to the time to which the fault will exist in the system. Yeah, listen here. So two types I'm saying. First one, it's a momentary fault, or you can say transient fault. Momentary fault, or you can say transient fault. Momentary fault, or you can say it's a transient fault. Right? Meaning of this momentary fault or transient fault is simply the fault will exist for a very short amount of time in the system. Means fault will occur in the system. Fault will occur. And it will clear on its own. Fault will occur in the system and it will clear on its own without opening of any breaker. Okay. So this fault will exist. It is a fault which exists for a short amount of time. It is a fault which exists exists for a short amount of time. Short amount of time in the system. It exists for a short amount of time in the system, or it will be cleared on its own. This fault, it will be cleared on its own. It will be cleared on its own. It will be cleared on its own. And sometimes you can call this fault as a self-clearing fault also. It can also be called as self-clearing fault. Self-clearing fault. Cleared on its own, or we are naming this as self-clearing fault. Okay, like as an example, I will tell you. For example, you see transmission lines. These may run in forest most of the times, particularly 400 kV lines and 220 kV lines. 400 kV and 220 kV lines may run in forest, right? So generally we used to have large length of snakes in forest, large size or large length of snakes in the forest. Unfortunately, if the snake falls on two conductors in the three-phase transmission line wire, if a snake is falling on two conductors, then we experience a short circuit between two wires with a snake. Snake is a fault element. Snake is a fault element. So definitely that snake will carry a large amount of current. Snake will carry a large amount of current, so-called fault current. So with effect of that current, definitely that snake will die. And after the snake gets died, it will get burned. And after it gets burned, it will cut into two pieces. Whenever it cuts in two pieces, obviously fault is getting cleared on its own. Following what I'm saying, right? So if a snake falls on two conductors, snake falls on two conductors, right? It will carry a huge amount of current, creating a fault, and it will get died and gets burned out. Whenever the snake gets burned out, it may cut into two pieces and fault is going to be cleared on its own. And that's the best example we can say for the self-clearing fault in the system. And other type of fault is a permanent fault in the system, or sustained short circuit fault in the system. Maybe falling a tree branch on transmission line wire. If a tree branch has fallen on the transmission line wire, the tree branch may not get burned, out. So it will persist for a long amount of time in the system. And within the time, our system may get damaged. So we have to clear the fault on our own with the help of a circuit breaker. Okay, so I can say the second one will be permanent fault or sustained fault. So it is a fault which exists for a long amount of time in the system. Long amount of time in the system. Long amount of time in the system. And it has to be cleared by circuit breakers. Or it has to be cleared manually. It has to be cleared manually. Manually clearing faults. Yeah, sometimes that momentary fault or transient fault can also be called as temporary fault. Temporary fault, you can say. Temporary fault. Okay, so we stop at this point. We continue with different types of short circuit faults and what are the practical reasons to get short circuit faults. All these things from tomorrow onwards. Okay. So you can raise your hands if you have anybody having a doubt. You can raise your hands if you have a doubt. Pujar.
Sir, 84.
I don't have that now. Okay, tell me what's the doubt you have in that.
Sir, actually in that the zero sequence network you had given one question the bus 1 and the bus 2 gets disconnected, sir. So why it happens? Like the midpoint question, sir.
Midpoint question. Okay.
Sir, in that, basically, what was the question was two generators are given and then one transformer is given. Two generators
Okay.
and one
Okay.
bus.
Where at what location you have a doubt? Tell me, please.
Sir, at bus 1, while drawing the zero sequence network, how does the connection between bus 1
What is the
and the
transformer connection you have beside to bus 1?
delta, sir?
Okay. Delta means what? Delta means which switch you have to close in your zero sequence network. Delta means, are you listening to me, Pooja?
Hello.
Are you listening to me?
Yes, sir.
Delta means which switch we have to close, shunt or series?
Sir, series we have to close.
Okay. And go through the previous class what we have discussed once. Delta means you are saying series switch to be closed.
Okay, sir. Got it, sir. Got it, sir. So shunt we are closing and then series we are opening, sir.
Any other doubt you have, Pooja?
No, sir. No, sir.
Yeah. Prithviraj.
Hello, sir.
Tell me, Prithviraj.
Sir, we did for sequence networks of three-phase transmission line.
Okay.
We have taken this voltage drop equation, sir. Sir, when we are taking voltage drop equations, mutual inductance is coming into picture, sir.
Yes.
Sir, if a voltage drop of a system should be depending on the current of that system only, or current of that phase only, sir.
Definitely, other conductors will have some mutual induced EMF, right? Other
Yes,
conductors
sir.
will cause for some mutual induced EMF.
Okay, sir. Means
But mutual induced EMF also we have to consider while we are dealing with that.
yes, sir. Means my doubt is IA is flowing in the line, and these ZM and means ZBB, ZCC also means ZJB and ZBC also should be linked with IA. I am thinking.
Obviously.
But in equations we wrote like IAZS plus IBZM plus ICZM.
What is that ZM?
ZM is mutual inductance.
Mutual inductance. What's the doubt you have in that then?
I am saying in
clear,
place of IB, it should be IA. I am saying, but I don't.
If it's IA, it will be again self only.
Okay, sir.
If it's IA, you write, that will be again self, right?
Yes, sir. But IA into ZM, I am saying it's not
IA
happening.
into ZM, if you write, this also IA into ZM. IA, you can take common ZS plus 2 ZM, you get there.
Yes, sir. That's what I am thinking.
How you write it? If it's a mutual induced EMF, you have to take the mutual linkages between the other conductor to the conductor where you are calculating.
Okay, sir.
Who will
Means
decide it? The current flowing in the other conductor will decide how much is the induced EMF we have.
okay. In terms of induction, this thing is reducing the
Induction only,
voltage.
right? We are talking about induction only here, mutual induction.
Okay, sir. And one more thing is, sir, this unsymmetrical and untransposed system is there, na, sir? Where all the impedance network is getting disturbed. In which, by using which ways we will solve that, sir?
For that again you have to do ABC analysis only.
ABC analysis only.
ABC analysis only. In some textbooks, the people will write, they will use these unequal impedances and they will find out this network.
Okay, sir.
Okay, after finding this network, what they will do is they will neglect these numbers. These non-zero numbers you get right in the half diagonal.
Okay, sir.
These numbers they will neglect and they will say this number is Z0, this number is Z1, this number is Z2.
Okay, sir.
Like that you can do, but that's an approximate study. It's not exact.
Okay.
Okay, and some people will try to define by keeping impedances here and whatever you get number here, that itself is Z0.
Okay, sir.
So that's not exactly Z0. The zero sequence effect depends upon the positive and negative sequence also in that case.
Means in exams, this unbalanced and unsymmetrical.
Generally, we don't get. Generally, we don't get. We don't get.
That's
But
it.
we have this concept in textbooks.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.
Any other doubt you have, Prithvi?
That's it, sir.
Ashish Raj.
Hello, sir.
Tell me.
Sir, about this power factor decrease in short circuit, sir. Means if power factor is decreasing, means that magnetizing current, sir, it increases, sir.
I don't say
Hello.
magnetizing current. Why you are calling magnetizing current here, Ashish?
Sir, that active and
Net
reactive
current-
power, sir.
Net current is reactive in nature, we will say. It's not a magnetizing current.
Okay, that's what I was thinking, because the frequency is also, sir, decreasing. Means overall, sir, means ऐसा है कि सर मतलब वहां से ये जब स्पीड कम हो रहा है, तो सर स्पीड कम हो रहा है, तो सर इसका मतलब सर एक्टिव पावर कम हो रहा है, सर.
स्पीड कम हो रहा है बोले तो एक्टिव पर कम होता नहीं, वो रिलेशन सही नहीं,
Okay, that means
वो रिलेशन सही नहीं. हमारा नेटवर्क प्योर रिएक्टिव से कन्वर्ट करेगा. Because of fault, our network was completely converted to reactive.
okay, sir.
Then it is drawing obviously reactive current.
Okay, sir.
But you should not say it's a magnetizing current. Magnetizing current, that's a different name we will use in induction machine and transformer.
Okay, so this means that it is using that reactive current.
Network is reactive in nature, drawing lagging current. That's it.
Yes, sir. Yes, sir. Okay.
Any other doubt you have?
No, sir. Not right.
Yeah, fine. Thank you. Kumar. Kumar. Do you have any doubt, Kumar? Kumar, are you there, Kumar? Do you have any doubt? Okay. Tulasi.
Hello, sir.
Tell me, Tulasi.
Sir, in 77F, sir.
Okay.
Sir, not 1 minute. Sir, in 71F, sir.
Okay.
Sir. ఇక్కడ ఇప్పుడు మనం బ్యాలెన్స్డ్ నెట్వర్క్ క్యారింగ్ అన్బ్యాలెన్స్డ్ వోల్టేజెస్ అండ్ కరెంట్స్ అన్నాం కదండి సార్. కాబట్టి ఇప్పుడు ఆ అనాలిసిస్ అదొకసారి చెప్తారా సార్ అక్కడ పాయింట్ ఎక్స్ప్లెయిన్.
When these symmetrical components will be useful to us. Your network should be in a balanced mode, but it's carrying unbalanced voltage and currents.
Okay, sir.
If the network itself is unbalanced one, you can't draw per phase positive sequence network, per phase negative sequence network, and per phase zero sequence network.
Yes, sir.
That's why you are getting that coupling there in the previous slides. This coupling you are getting from one another. Okay. So
Yes, sir.
when the symmetrical components will give an advantage means network should be balanced. Means your generator, transformer, transmission line should have equal impedances in the phase A, phase B, phase C.
Yes, sir.
But those are carrying unbalanced currents because of the load.
Those are, yes, sir.
Okay. In that situation, the symmetrical components will help us to solve the system for currents.
Okay.
Okay.
Got it.
Yeah. Any other doubt you have, Tulsi?
Yes, sir. 81F, sir.
81. Okay.
Sir, పేజ్ నెంబర్ ఇప్పుడు ఒక క్వశ్చన్ అడిగారు సార్. 3-phase సిమెట్రికల్ స్పేస్ ట్రాన్స్మిషన్ లైన్ హ్యాస్ 4 wires ABCN.
Okay.
సార్ ఇప్పుడు ఈ క్వశ్చన్ కి ఫస్ట్ లో ఎక్స్ప్లెనేషన్ ఇచ్చిన దానికి డిఫరెన్స్ ఏం సార్? ఇక్కడ మనకి ఎందుకు సార్
Earlier we didn't consider the neutral wire.
సార్ అక్కడ మనము రెఫరెన్స్ గ్రౌండ్ తీసుకున్నాం కదా.
Reference is ground. Ground impedance is 0.
ఓకే సార్.
But now we are keeping specially one neutral wire here.
ఎస్ సార్.
So the 3 times of Zn should be added to Z0.
ఎస్ సార్. ఓకే సార్, గాట్ ఇట్.
Any other doubt you have?
సార్ ఎస్టర్డే క్లాస్ లో ఒక డౌట్ ఉంది సార్ నాకు.
Tell me.
సార్ మనం ఫస్ట్ లో క్యాలిక్యులేషన్స్ చేస్తున్నప్పుడు వి బేస్ పర్ ఫేస్ తీసుకున్నాం కదండి సార్.
Yes.
అది ఎందుకు తీసుకుంటున్నాం సార్? అంటే లైన్ టు లైన్ తీసుకొని అది చేసి ఉండొచ్చు కదండి సార్ మనము. బ్యాలెన్స్డ్ సిస్టమ్ అని చెప్పి
What you want to do here?
It-
What type of analysis you want to do?
బ్యాలెన్స్డ్ సిస్టమ్ సార్.
Okay, which analysis you want to do? Three-phase analysis, per-phase analysis?
3 phase అనాలిసిస్ సార్.
Per-phase, right?
ఎస్ సార్, పర్ ఫేజ్.
What circuit you are drawing? Per-phase or line to line?
పర్ ఫేజ్ ఓన్లీ సార్.
Per-phase means which phase you have to consider?
పర్ ఫేజ్.
That's it.
ఓకే సార్. కాదు సార్, ఫస్ట్ లో మనము డెరివేషన్స్ తీస్తున్నాం సార్ ఇక్కడ. మోడ్ ఆఫ్ విఏబి ఇన్ కిలో వాట్స్ ఇస్ ఈక్వల్స్ టు
Hmm.
వాట్ వి గాట్ ఇన్ విఏబి పర్ యూనిట్ ఇంటూ వి బేస్ పర్ ఫేజ్ సార్.
Okay.
అక్కడి నుంచి మనం డిరైవ్ చేసాం సార్. అక్కడ వి బేస్ పర్ ఫేజ్ ఎందుకు వేసుకున్నామని నా డౌట్ వచ్చింది.
Because you are taking VA per unit minus VB per unit on your calculation.
ఎస్ సార్.
VA per unit we have to multiply with V base per phase to get in kilovolt.
ఎస్ సార్.
VB per unit you should multiply with V base per phase to get in kilovolt.
ఎస్ సార్.
So V base per phase is common.
ఎస్.
VA per unit minus VB per unit into V base per phase is a perfect one to calculate VAB line. VAB
Okay.
in kilovolts.
గాట్ ఇట్.
Okay.
థ్యాంక్ యూ.
Okay. Fine. Any other doubt you have, Tulsi?
నో సార్.
Imtiaz. Imtiaz.
Good evening, sir.
Yeah, tell me, Imtiaz.
Sir, I have doubt in this problem, sir.
Hmm.
Sir, you said that first assumption is that no leakage, no mutual leakage
Linkages
between the
between the
neutral wire
neutral wire and
phase
ABC.
conductor.
Hmm.
One more assumption is also there, sir. Mutual leakage impedance exists between two wires.
Mutual.
Mutual leakages exist between neutral wire and the phase conductor.
If you have that mutual linkages, that will be again added with this Z0.
Extra Z0.
Extra, some more number will be added at that
But
time.
in question, it's not mentioned, no, sir.
It's not
not-
mentioned, but it's a reasonable assumption to take. Because if that is mentioned in the question, if they have to give that neutral to ABC mutual impedance, that they should give in the data.
Means before 2-3 classes, we said no, sir, two mentions we are taking assumption 1, assumption 2. In that,
Listen. For example, if you have linkages between the neutral wire and ABC wires, are you listening to me, Imtiaz?
yes, sir.
Yeah. If you have a linkage between neutral wire and ABC wires, that impedance will come in the portion of the Z0 equation.
Extra.
Extra, some term is getting added here.
Okay, sir.
Okay, that term you don't know, right? Then we
Yes,
can't
sir.
solve the problem
Yes.
because that value they have not given the problem. So as they have not given that value in the problem, I will assume that it is 0.
Okay, sir. Sir, normally mutual inductance occur between two conductors, no, sir. If we have
Any two
neutral,
conductors.
if you have neutral, there is no conductor, no, sir.
If you have neutral wire, it is separate
Yeah.
wire.
Separate wires have no conductor, no, sir.
Separate wire we mentioned, right?
Okay. If you have ground, there is no mutual inductance.
It's a 3-phase 4-wire system.
Yes, sir. If you mention ground, there will be no mutual inductance
There
between
will
the phase and ground.
be this 3 ZN will go 0.
Yes, sir. Sir, one more doubt is,
Hmm.
normally we are using the symmetrical analysis for the unbalanced system, no, sir.
Okay.
Unbalanced means we have
Voltages and currents are unbalanced.
unbalanced and phase difference also unbalanced, no, sir.
Maybe.
But before after this problem we said no, sir. Unbalanced means only voltages and currents are unbalanced for the 3-phase balance system.
Okay.
But
What's
in
the doubt?
but in the question they are directly mentioned, no, sir. Unbalanced system.
Okay, unbalanced system. Okay.
What we consider, voltage and current will be different more than else we are consider.
I didn't get you. In which question you are asking me?
Normal question, sir. Any of question.
Okay. Any of the question? What they have mentioned, tell me please.
అంటే క్వశ్చన్ లో ఏమన్నా అన్బ్యాలెన్స్ సిస్టమ్ అడగదా సార్?
Okay. They have given the system as unbalanced.
it means voltage and currents are unbalanced.
Voltages and currents are unbalanced. Okay,
Yes.
fine, good, good.
At that time we are using symmetrical analysis.
Symmetrical analysis. Okay.
But you said not, no, sir. అంటే ఒక
If voltage and currents are unbalanced, that does not mean that your network is unbalanced, right?
it's maybe no, sir.
Network is balanced. Your generator, transformer, line, these are having equal impedances in the phase A, phase B, phase C. But those are supplying an unbalanced load.
Oh, okay, sir.
Because of that, the voltage and currents in the system are becoming unbalanced.
Yes, sir.
Your generator will have equal impedance in phase A, phase B, phase C, but it is supplying unbalanced currents.
Okay. అంటే based on unbalanced load we are changing.
Yes.
Okay, sir. That's all, sir.
Any other doubt you have, Mukesh?
No, sir. Thank.
Okay. Vaishnavi.
సార్ ఇన్ కాన్సిక్వెన్స్ ఆఫ్ షార్ట్ సర్క్యూట్ ఫాల్ట్ లో ఒకటి చెప్పారు కదా సార్, పవర్ ఫ్యాక్టర్ లో ఉంటదని. ఆ పాయింట్ ఒకసారి మళ్ళీ చెప్పారా సార్? అది
What is the power factor of system during short circuit?
లో అని చెప్పారు కదా సార్.
What is formula?
V/I సార్. హలో,
Tell me.
పవర్
What is the
ఫ్యాక్టర్
formula for power factor in the short circuit condition?
పవర్ బై V into I no sir. Power factor.
Just see the notes. I have said something.
Yes. Okay sir. Theta is equal to tan inverse of XL by
Cos theta.
R.
Cos theta is a power factor.
Yes sir.
How is theta? Theta is tan inverse of x by r.
Yes sir.
X by r ratio of line. But generally that's
yes.
very high. X by r ratio of line is very high.
కానీ జెడ్ అనేది తక్కువ ఉంటదని చెప్పారు కదా సార్. జెడ్ అనేది చాలా
That value
తక్కువ.
may be low, but angle will be high.
ఓకే సార్. సార్ మరి 101 సార్.
101. Okay.
సరే, ఇక్కడ ఇప్పుడు కరెంట్ T1 లోకి వచ్చి అది మళ్ళీ G2 G1 లోకి పాస్
ఎట్లా
అవ్వదా?
ఇక్కడ ఓపెన్ సర్క్యూట్ ఉంది కదా?
కింద నుంచి వచ్చి సార్ రెడ్ వైర్ నుంచి ఫ్లో అయ్యి ఇట్లా
So down it's flowing.
ఎస్ సార్. డౌన్
It's
వచ్చి
flowing down. Then
లెఫ్ట్ సైడ్ సార్.
left side. Okay.
ఇంకా G2 కి G1 కి అట్లా వెళ్ళదా సార్?
How it will go?
సార్ నేను డౌట్ వస్తుంది సార్, అట్లా వెళ్తుందా వెళ్ళదా అని.
If current is leaving from this point to down like this,
Yes.
okay, that current should come back to the same place, right?
What sir? Again sir.
If some 10 amperes current is going out, something like this,
Yes sir.
by some way the 10 amperes current should come back to this node, right?
Okay sir, but it is
So
not
this 10
coming.
amperes is entering. How it is going in this G1 G2? It's a single impedance. You can take if you want parallel combination,
Yes sir.
and it's open circuit, right?
Yes sir. Yes sir.
And it won't carry any current.
Okay sir.
Okay, just basic network analysis concept.
సార్ మళ్ళీ ఒక చిన్న డౌట్ సార్, న్యూట్రల్ కి గ్రౌండ్ కి డిఫరెన్స్ ఏంటి సార్?
What is ground?
గ్రౌండ్ జీరో పొటెన్షియల్ సార్.
Ground means on which we are standing. Sir,
Yes sir. Yes sir.
that's the ground. We are assuming that potential is zero.
Yes sir.
What do you mean by neutral?
Sum of currents.
Junction of the three windings in the
Yes
star.
sir. Yes sir.
That's it. That's the difference.
అంటే ఆ రెండిటికి సిమిలారిటీ అట్లేం ఉండదా సార్? సిమిలారిటీ
No similarity. Whether we connect that neutral to ground or not, that is our decision.
సార్ మరి
Similarity you should not say. Similarity you should not say. Neutral means in our analysis, it is simply junction of three phases.
ఓకే సార్.
Junction of three phases is called as neutral. Three phase
Okay.
winding.
ఓకే సార్.
Ground means it's a earth on which we are standing.
ఓకే సార్. సార్ మరి అన్సిమెట్రికల్ ట్రాన్స్పోజ్డ్ అంటే మీనింగ్ ఏంటి సార్?
That will come in T&D. We'll discuss that in T&D.
ఓకే సార్
Okay,
మళ్ళీ
for timing, just you remember that word. We'll discuss that at the end.
ఓకే సార్ ఇవి మామూలుగా ఏబిసి ఫేస్ కరెంట్స్ ఉంటాయి కదా సార్ వాటిని మనం అన్సిమెట్రికల్ కరెంట్స్ అని అనొచ్చా సార్
Asymmetrical currents.
అని నేమ్ ఇవ్వచ్చా సార్ ఫేస్ కరెంట్స్ అయ్యే అన్బ్యాలెన్స్డ్ కరెంట్స్ ఉన్నాయి సార్ అయ్యే
Unbalanced currents can be called as asymmetrical currents
ఓకే
or
మరి-
unsymmetrical currents.
ఓకే ఇంకో చిన్న డౌట్ సార్ కపుల్డ్ ఈక్వేషన్స్ అంటున్నారు కదా సార్ అంటే మీనింగ్ ఏంటి సార్
Coupled equations means, for example, if you have three ABC equations, right? Phase A voltage drop, phase B drop, phase C drop.
ఎస్
Can we solve only phase A voltage drop equation first?
వాట్ సార్
Phase A voltage drop equation itself can we solve?
నో సార్
Why? Because we have many unknowns in that.
ఎస్ సార్
Who will decide the solution of that equation? Second equation.
అదే సెకండ్ ఈక్వేషన్
Obviously, the three equations are having some common terms like IA, IB, IC.
ఎస్ సార్
So obviously, we say the three equations are coupled together, right?
ఓకే
Okay.
ఓకే
Right. Any other doubt you have, Vaishnavi?
సార్ నో సార్ క్లియర్ సార్
Okay. Okay. Yogashri,
సార్
tell me, Yogashri.
సార్ ఇక్కడ మనము జీరో అనేసి జీరో సీక్వెన్స్ కరెంట్ అనేది లైన్ 2 అండ్ టీటీలో కూడా వస్తుంది కదా సార్
Why?
సార్ ఒకసారి
tell me why.
జీరో సీక్వెన్స్ ఎలా తీసుకున్నారు ఒకసారి చెప్పారా సార్ నాకు అర్థం కాదు
Just we are injecting some current here.
ఓకే సార్
After injecting some current, this current is seeing three paths to flow.
ఓకే
One path is through T1, and if you go along with this T1, is it circulating back to this current source or not?
ఎస్ సార్
Yes. So T1 will carry the current.
ఓకే
And second path, I am going with line 2. I am tracing line 2, T2, G3, but I am experiencing open.
ఓకే నైస్ సార్
So whatever the current flowing in the line 2, it's not coming back to source, right?
ఎస్ సార్
Means this current will be zero, obviously.
ఓకే సార్ అండ్ లైన్ 1 is coming from neutral to ground.
Line 1 is carrying current. Motor is carrying current,
Okay.
and that is grounded.
Yes, sir. Okay.
Grounded means it can circulate back to source.
Okay, sir.
So whatever the current it is delivering, the same current should enter from bottom end, right?
Yes, sir. Okay, sir. I understood, sir.
Okay.
Yes, sir.
Yeah. Any other doubt you have, Yogashri?
So, Z1, ZS, ZM మనం తీసుకున్నది కదా సార్ ఇట్లా మ్యాట్రిసెస్ ఫామ్ లో
Yes.
అది ఒక్కసారి కొంచెం చెప్తారా సార్ అది కూడా కొంచెం అర్థం
What's the doubt you have in that?
మ్యాట్రిక్సెస్ లో మీరు 1 ZS Z సీక్వెన్స్ లో 1 2 3 అని అట్లా ఇచ్చారు కదా సార్ అక్కడ నాకు అర్థం కాలేదు సార్
See, actually, if you are having all these three mutual impedances equal, ZM, 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 okay, if you do this matrix multiplication, you will get zero values in the half diagonal. Okay, but if these mutual impedances are becoming unequal, you don't get zero values in the half diagonal. Understanding what I'm saying? You,
yes sir.
if these three mutual impedances are equal, then half diagonal numbers will be zero. But if these three are unequal, means half diagonal numbers will be non-zero. Again, the resultant three equations, what you get in the symmetrical components, are depending on one another.
Yes sir.
Please tell me if you have any doubt, Yogashri.
సార్ ఇక్కడనే అంటే ZS ZM1 అట్లాగా తీసుకునేసరికి అక్కడ కన్ఫ్యూజ్ అయ్యింది సార్ అర్థం కాలేదు అందుకనేసి అడుగుతుంది
Okay. Are you clear now?
సార్ బట్ ఇక్కడ 1/3 అంటే ఇక్కడ తీసుకున్నారు కదా సార్ ఆ ప్రాసెస్ నాకు కొంచెం అర్థం కాలేదు సార్ అందుకని అడుగుతున్నాను
1/3. See, actually, first we have taken equal mutual impedances. We have done the analysis. Yogashri, are you there?
ఎస్ సార్ ఎస్ సార్
First, we have taken equal mutual impedances. We have done the analysis. That is over. Second case, we are taking unequal mutual impedances. If mutual impedance are unequal, what will happen? That we are investigating here.
Okay, sir.
If mutual impedance are equal, then we are getting positive sequence equation separate, negative sequence equation separate, and zero sequence equation separate like this. But if mutual impedance are becoming unequal, the three equations are coupled together. Means zero sequence voltage drop depends upon zero sequence current, positive sequence current, as well as negative sequence current also.
Okay, sir.
But if mutual impedance are equal, zero sequence voltage drop depends upon only zero sequence current.
Okay.
So if mutual impedance are becoming unequal, I am not getting any advantage of using the symmetrical components. Because earlier ABC equations are depending on each other, and symmetrical component equations also depending on each other. That's a disadvantage. I am unable to get any response from you, Yogeshri.
Sir, unsymmetrical line and untransported అన్న కూడా ఒకటేనా సార్?
Unsymmetrical transposed is one category.
Okay.
Unsymmetrical untransposed is the other category. Yeah, please kindly respond, Yogeshri.
Yes, sir. Understood.
Have you understood that?
Yes, sir.
Okay. Any other doubt you have, Yogeshri?
No, sir.
Can I mute you?
Yes, sir.
Yeah. Charan Reddy. Sai Charan Reddy.
Good evening, sir.
Good evening. Tell me.
Sir, sir, here only, sir. Sir, in this one only, last statement you gave now, sir. In this one only.
Next slide or this slide only?
In this topic only, sir. Next slide, I think, sir.
Okay, tell me.
Yes, sir. This sir. Symmetrical component will be this one, sir. This, sir. So, if they carry or if they supply for unbalanced loads, then the unbalanced voltage and currents will be carried through the source, na, sir. So overall, the source will be unbalanced only, na, sir.
Induced EMFs will be balanced, right?
So here we should not take this unbalanced voltage and current, sir.
Induced EMFs are balanced. Terminal voltages of alternator are unbalanced.
We will not get half of the matrix as non-zero, sir, if you do like this.
Half of the matrix is non-zero. I didn't get.
You explained.
See, you have a doubt. You have a doubt that. Sir, you said it's carrying unbalanced voltage and currents. That's okay. If it's carrying unbalanced voltage and currents, definitely induced EMFs will be unbalanced, right? Is it your doubt?
No, sir. My doubt is that if they carry unbalanced voltage and currents, then I'm thinking that the system is carrying unbalanced voltage and currents, so the system is unbalanced. And how we can apply the symmetrical components so that we will get.
Okay. What you want to construct? Positive sequence network, negative sequence network, and zero sequence network, right?
Yes, sir.
Whether you construct that with load or without load.
Okay, so without load, first we do and we will analyze, sir. Okay.
Then we will give the connections according to the loading condition.
Okay, sir.
Okay.
So before connecting any system to load, we will analyze total system and then we connect that load, sir.
Yeah, correct. That load means if it is an unbalanced one, like a fault or something you have, before doing fault analysis, first you should be ready with the positive sequence, negative sequence, and zero sequence networks.
Okay.
According
So
to the type of fault or according to the type of unbalance, we have to give connections.
So we will forecast. We will forecast before only about that sequence, sir, positive, negative, and zero sequence.
Obviously, while you are going for the breaker design and all, first you should do some theoretical fault analysis on the system.
Okay, sir. Like up to what extent the positive sequence current would be, up to negative sequence, like that, sir.
Yes.
Okay. Sir,
if it is occurring at particular bus bar, how much will be the sequence current?
Okay, sir.
So that analysis we have to know, based on which we are going to design the breaker, right?
Okay, sir.
Okay.
Sir, can we give this transformer inrush current, sir? When switching happens, like power will go and come again, sir, in some speed. Then the switching of transformers, then the inrush current will be treated as temporary fault, no, sir?
No, we don't treat it as a temporary fault.
Inrush current will be high and it is like fault current in protection. That's SART set, sir.
Okay.
So we should
We
treat
should
that.
not say that as a fault. Means describing that as a fault, I don't think so. You say it's an abnormality. That's it.
Yes, sir. Abnormality. Yes, sir.
Say abnormality. We have an abnormal operating condition. That's it.
Yes. Okay. Sir, can you please mention again that unsymmetrical, untransposed, and unsymmetrical transport? Here,
line is
unsymmetrical
unsymmetrical. Line is unsymmetrical. Listen, Sai Charan.
Yes, sir. Yes.
Line is unsymmetrical. If you don't transpose the line, then mutual impedance are unequal. If you transpose the line, then the mutual impedance are equal.
Yes, sir. So transpose means keeping in a triangle form.
Changing the position of conductor with respect to length.
Okay, sir. Is unsymmetrical transposed is a balanced one, sir? Unsymmetrical transposed. We should treat it as
balanced network, because phase A, phase B, phase C will offer equal impedances per positive sequence.
Balanced line or balanced total network, sir?
Network. Only line network is balanced. Not whole system. May not be. Whole system depends upon remaining equipment also, right?
Line means a transmission line between two bus bars. We will treat it as
it's a symmetrical network. It's a symmetrical network.
No, sir. I am asking that we are talking about that one only, sir. Transmission line between two bus bars. Okay, sir. Then balancer means we will treat apparatus like generator, transformer. We will name it as balancer or unbalanced. But for lines, we'll
say balanced only. That is also balanced network only. Transmission line also balanced network.
Okay, sir. Okay, sir. Sir, please open once 74F, sir.
Okay.
Sir, in this, someone asked that leakage impedance, but due to network connection, I did not understand your explanation.
What he said is, how can you say we don't have any mutual linkage between neutral wire and ABC wires? He made one assumption in the next slide, right? No mutual linkages existing between the neutral wire and phase conductors.
Yes, sir. Yes, sir.
Okay, why we have made that assumption means they have not given that number in the data.
Okay, sir. If they, in case if they give, then what
this
about
Z0 equation has to be modified little.
Sir, can you please show in the 75, sir, in next page?
Okay.
Where do we?
So this Z0, we have ZS plus 2ZM plus 3ZM, right?
Yes, sir.
And you get some additional term here. Some more term, additional term we are going to get if you have mutual linkages between neutral wire and the phase wires.
Okay, sir. Okay, sir.
But as they have not mentioned it, as they have not given in the problem, we will assume that no mutual linkages between neutral and the phase wires.
Okay, sir.
If you consider those mutual linkages, if you get that additional term, we can't solve the question, right? Because you don't know that number.
I thought that we will add that in 2ZM. I thought, sir, that.
No. It's not in 2ZM. ZM is mutual between phase conductors only.
Okay, sir. Okay.
Okay. Any other doubt you have, Sajara?
No, sir. No, sir.
Yeah. Thank you. Anil Kumar.
So good evening, sir.
Good evening, Anil.
Sir, in this page, that how we added 3 ZN, sir, zero sequence.
We discussed that in general transformer, sorry, that alternator and all, right? We have 3 IR current flow in the ZN.
Yes, sir. Yes.
By applying KVL for phase A. By applying KVL for phase A, IA naught into you get ZS,
Right,
and then you
sir.
have IA naught, 3 IA naught into ZM.
Right, sir.
Okay.
Sir, yes, sir. That's okay, sir. Here we are, how we are added. That's I am doing.
That's what I am saying you again by applying KVL between A and neutral. In the zero sequence
sir,
current, you have to apply KVL between A and neutral, right?
Okay, sir. Okay, I got it, sir.
Okay.
Yes, sir.
Mhm.
Sir, thank you, sir.
Any other doubt you have, any?
No, sir.
Okay, fine.
Thank you, sir.
Pratyush,
హలో సార్
tell me, Pratyush.
సార్ ఇన్ కేస్ ఆఫ్ అంటే ఆల్టర్నేటర్ సీక్వెన్స్ నెట్వర్క్ కన్స్ట్రక్షన్ లో నెగిటివ్ సీక్వెన్స్ యొక్క కన్స్ట్రక్షన్ కి మనం ఈఎంఎఫ్ అనేది 0 వచ్చింది కదా సార్ అనాలిసిస్ చేస్తే కానీ కరెంట్స్ అనేవి క్యారీ చేస్తాయి కదా సార్ అంటే అది అనాలిసిస్ మాత్రం కాబట్టి ఈఎంఎఫ్ లేకపోయినా కరెంట్స్ అనేవి క్యారీ చేస్తున్నాయని అనుకోవాలా సార్?
You have a balanced source and you are keeping unbalanced load on that.
ఎస్ సార్ అంటే ఈఎంఎఫ్ అంటే సోర్స్ లేదు కదా
Current supplied by the generator depends on its own or depends on the load.
డిపెండ్స్ ఆన్ ద లోడ్ సార్ కరెంట్.
That's it. According to the load demand, it has to supply current.
ఎస్ అంటే నా డౌట్ ఏంటంటే సోర్స్ లేకపోయినా నెగిటివ్ సీక్వెన్స్ అనేది డ్రా అంటే కరెంట్ డ్రా చేస్తుంది కదా సార్, లోడ్ వల్ల డ్రా చేస్తుంది కదా సార్.
Actually, the generator fellow don't know about negative sequence, positive sequence, right?
ఎస్ సార్
He knows only IA, IB, IC.
ఓకే.
Okay, so you should not say a statement that zero sequence is not supplied by generator, it is created by the system on its own. That statement we should not say actually. It is flowing in the generator. It's flowing in the generator. Is it contributing to any power or not? That is the secondary thing.
Okay.
So power is a power supplied by generator is a main thing what you have to consider.
Okay, sir.
Okay.
ఎస్ సార్. సార్ ఇక్కడ ఇప్పుడు ఈ ట్రాన్స్మిషన్ లైన్ కి 3Z అని చెప్పారు కదా సార్. సార్ కానీ మనం ట్రాన్స్మిషన్ లైన్ అనేది డెల్టా స్టార్ చెప్పలేము కదా సార్, అంటే 3Z అని ఎలా తీసుకోగలిగాం సార్?
So these are 3 wires ZS carrying a current of IA0, carrying IB0 current. ZS mutually is ZM, and it is IC0, ZS, and this mutual is again ZM. This mutual is ZM. These are ABC wires, and it is your neutral wire. Okay.
Yes, sir.
Whatever the current you have, IA0, IB0, IC0 summation flowing in this direction, 3 IA0. Okay.
Okay.
And this is a voltage at this terminal as VA0. And this is the voltage at this terminal as VA0 dash. What is VA0 minus VA0 dash?
3IA0 into
you come from phase A. IA0 into ZS is self drop.
Yes, sir.
IB0 into ZM is a mutual drop due to B.
Yes, sir.
IC0 into ZM is a mutual drop due to C.
Yes, sir.
And then there's a total A drop, phase A drop.
Yes, sir.
And then you have plus 3 IA0 into ZM.
Yes, sir.
Then if you take that IA0 common, you get ZS plus 2 ZM plus 3 ZM. So this is an impedance which is causing for zero sequence voltage.
Sir, this means the load is also connected through this neutral, sir.
Why you are bothering about load? VA0 minus VA0 dash, that's it. See, if your load is not providing any closed path, then obviously IA0, IB0, IC0 will be 0.
Yes, sir.
Your circuit will act as open. That's it.
Okay.
Whether this current will circulate or not, that depends upon the other equipment what you connect to the transmission line.
Yes, sir.
If that is not providing, you assume first it is providing.
Okay, sir.
And you calculate it. And you keep that in the network. If it's not providing, automatically it will come down to zero. Means current.
Okay, sir.
Impedances will not come zero. Current will come zero.
Yes, sir. Sir,
Okay.
okay, sir. Sir, and sir, another doubt, sir. Sir, you said that network is balanced, but load due to unbalanced load network, it is carrying unbalanced currents and unbalanced voltage, no, sir. That means అంటే ఇప్పుడు అక్కడ ఇండ్యూస్ వోల్టేజ్ అనేవి రోటర్ యొక్క స్పీడ్ మీద డిపెండ్ అవుతాయి కాబట్టి ఇండ్యూస్ వోల్టేజ్ ఆల్వేస్ బ్యాలెన్స్డ్ అని తీసుకోవాలా సార్?
Yes, yes.
ఓకే సార్, దట్స్ ఇట్. థ్యాంక్ యూ.
Yogesh.
Hello.
Tell me, Yogesh.
Hello. Good evening, sir.
Good evening.
Sir,
Tell me.
Actually, I had a doubt in this consequences of open circuit conductor fault, sir.
Okay.
Sir, there was one point that when electromagnetic torque increases, then speed will, electromagnetic torque decreases, then speed will increase, sir. So that I did not understand, sir.
See, actually, prime mover torque is in the direction of rotor rotation. Because of that only the rotor is rotating.
Yes, sir.
Generally, electromagnetic torque will act in opposite direction.
Sir, that torque is means created by this stator or what, sir?
Stator.
Yeah. Okay, sir.
Okay.
Okay. Thank you, sir. Thank you.
Okay, fine. Kumar. Do I have any
Hello.
doubt, Kumar?
Yes,
Tell me,
sir.
Kumar. Tell me.
Sir, in the year ZS means self impedance, right?
Impedance.
Which is occurred due to the resistance of the line and flux due to the current in that
Self-inductance of.
self-inductance. Sir, is the as unbalanced load, self-inductance in each line is different, right? As unbalanced currents flow through the
That's why you are doing the positive sequence, negative sequence, zero sequence separate.
but here we taken ZS, ZA is equal to ZBB is equal to ZC.
That is self-impedance.
Yes, sir. In self-impedance, self-inductance is there.
Positive sequence, all the three will have equal self-impedance, right?
Overall, sir. Overall, I'm taking.
Not overall. Positive sequence, all the three will have equal self-impedance.
Okay.
Self-impedance depends upon the conductor size.
Sir, then what is the ZA? Can you divide into positive, negative, and the zero?
No, ZA is ZS itself I am considering in the equations.
Okay.
Okay, that ZS depends upon the size of the conductor.
Yes, sir. Size, only size, sir.
Only size of the conductor and length of course.
But self-inductance depends upon the current also, right? Flux.
No, if you take up that current, it will be converted into induced EMF.
We don't consider the flux, sir.
I will consider the flux. We are saying about impedance, right?
Okay. Then, sir, here we take a mutual inductance as because of flux linkages, because of another conductor.
Yes.
Then what we about flux linkage of self-conductor?
Flux linkages of self-conductor was taken care by ZS only, right?
That's I'm saying that flux linkage.
ZS into IA naught will be creating the voltage drop.
So
what is the formula for psi? What is the formula for flux linkage psi?
Psi is equal to N5 by
inductance into current.
Yes, sir. Inductance into current.
Current I am not taking now. I am taking only inductance here. With respect to current, flux linkage will vary, not the value of inductance, right?
Okay. Because of inductance, flux will vary.
Because of inductance. L into I is a flux linkage.
Okay.
Because of current variation, flux linkage will vary. We are assuming inductance is constant.
Inductance of all conductors is constant.
And it depends upon their size.
Okay. Sir, I have another doubt in yesterday class, sir.
Tell me, Kumar.
Sir, here zero sequence, because of zero sequence currents, there is no flux in the air gap. That's why they will not cause any, that means, what's the
No armature reaction.
No armature reaction. Sir, zero sequence currents are flow through in starter, right?
Yes.
If any current flow through the conductor, there should be a flux according to, I think, Oster.
Okay, whatever it is. Okay.
So that flux will interact with rotor flux.
A, B, C, all the three are producing flux.
Yes, sir. ABC. Sir?
A, B, C, all the three are producing flux.
Yes, sir. There three are
Then
producing
that
flux.
resultant flux is zero.
Sir, is that zero sequence flux zero?
Total overall means resultant zero. The resultant flux due to ABC currents will be zero in case of zero sequence.
Sir, how, sir? They are not phase displaced by 120, but they are same magnitude and same phase.
Same phase.
Then the sum of the same magnitudes and same phase are zero. We don't get right.
If you sum up all the three fluxes A, B, C together, that will come to be zero. I am saying.
ABC means overall, right? Positive.
Overall, not positive. Only in case of zero sequence. We have zero sequence phase A flux, zero sequence phase B flux.
So that one we called as phi A naught, phi B naught, phi C naught.
Phi C naught. And if you sum up them, that will come to be zero.
Sir, they are caused because of phi A naught, IB naught, IC naught. Phi A naught, IB naught, IC naught is zero. Sum of the recurrence.
Inductances are there, right? Again.
Sir, I don't get it. Sir, can you availability explain in equation form or any phasor form?
It is a stator of alternator.
Yes.
This is a phase A conductor.
Yes, sir.
And A dash. Winding.
Yes, sir.
Okay, A dash. Coil. It's a coil. Coil of phase A. It's a phase B. I'm showing here. And it is B dash. Coil of phase B.
Yes.
And it is phase C.
Okay, sir, I got it. Because
And
of
it is
their winding 120 degrees phase displacement, so they are zero. That's why, because they will not cause any torque in the generators.
Don't say torque.
Right, sir?
No flux. Resultant flux will come zero. That's it.
That means in motors. Synchronous motors.
Okay, fine. In motor, it won't cause any torque.
Yes, sir.
Of course, in generator also you say, Mark,
yes,
you don't have any electromagnetic torque due to zero sequence.
Okay, sir.
Okay.
Sir, I have a small doubt. Star to delta transformation. Sir, we are converting star to delta to find the per phase network. Sir, we can't do in delta only. Is there any reason to convert? Means, is there any easy?
If it is delta, your phase winding is between two lines, right?
Yes, sir.
But you have to do your analysis only for phase A conductor.
Okay.
Only phase A conductor means phase A conductor to neutral you have to do, or phase A conductor to ground you have to do.
Okay.
Anybody have doubts? Please raise your hands. Muthireti Vasishtha, are you there? Muthireti Vasishtha. You are not waiting to the end till end, and again you are asking me, sir, please give me the time. Have I left any time? If anybody raised a hand, I think I didn't left the class without seeing that all hands as down. Okay, Kumar, do you have any more doubts to ask?
No, sir.
No?
Just I have, but
Then mute
I
you.
forgot it, sir. I will ask tomorrow, sir. I forgot.
Okay, Kumar. Okay.
Thank you, sir.
Okay. Ramakrishna.
Yeah, look, sir. So you have said that in a balanced network, due to unbalanced load, it will carry unbalanced voltage and current.
Yes.
So if it is balanced load, it will carry balanced voltages and current. That's it, no, sir?
Yes.
According to the load, it is changing. That's it.
It will get changed. Yes.
Balanced network has the property to change according to the unbalanced load.
Yeah. Mm-hmm.
That's it.
Okay.
Okay, thanks.
Mm. Muthireddy Vasishtha, are you there? You have not waited till the end to talk with you. Okay, fine. Anybody have doubts? Please raise your hands now. Anybody have doubts? Please raise your hands. Yeah, fine. So I think all of you clear. Thank you.